If you looked at the pillars of creation with your own eyes, you'd barely see anything. They'd look like empty space, cold, black, and silent. Inside that darkness, clouds of gas and dust are so dense they block visible light completely. These molecular clouds are the birthplaces of stars. They look calm from far away, but inside is constant chaos. So how does a star actually start from what looks like nothing? Almost all of the cloud is hydrogen, with helium and a sprinkle of elements like carbon, oxygen, and nitrogen. Dust, fine grains of silicate, carbon, and ice, adds crucial structure. The clouds are vast, frigid, and thin by Earth standards, yet over light years, that thinness adds up. Gravity slowly gathers the material into denser pockets. Over millions of years, the densest parts begin to collapse. Clumps heat as gravity squeezes them, marking the first spark of a protostar. Why one region collapses while another stays stable often needs a push. Shockwaves from supernovae or radiation from massive neighbours compress nearby gas. The battle between outward pressure and inward gravity decides the outcome. Because dust absorbs visible light, most of this happens invisibly. Infrared telescopes reveal the warmth of forming stars inside their cocoons. Radio telescopes trace molecules like carbon monoxide to map flows and turbulence. Together, they show a living landscape instead of stillness. The nursery is busy, messy, and always changing. Zoom in on a collapsing clump, and the picture sharpens. Density and temperature climb to extremes under relentless compression. Eventually, hydrogen nuclei fuse into helium and release enormous energy. That slow ignition marks the birth of a star. Radiation and stellar winds then begin to clear the leftover shroud. Now scale that up to thousands of newborns in a single region. That's the Eagle Nebula, with the pillars as one dramatic corner of a vast nursery. The pillars are dense columns being sculpted by nearby stars' fierce radiation. They look solid, but they're wisps held together by balance and gravity. Their pillar shape remains because surrounding, looser gas was blasted away first. Inside those columns, stars were forming when the light we see began its journey. Some may already have matured, and some may even have died. We won't know until their next chapter's light arrives here. Every bright speck and faint glow in the images is part of the same cycle. It's a long story of destruction feeding creation. This matters because it's the process that made everything. The iron in your blood and the calcium in your bones were forged in stars. Those stars themselves were born in clouds like these. We are literally the ashes of older suns. That realization is humbling and intimate. The pillars sit in the Eagle Nebula about 6,500 light-years away in Serpens. The nebula spans roughly 70 by 55 light-years, a true giant. Each pillar is a few light-years tall and holds enough material for hundreds of suns. Hubble's 1995 image made them iconic overnight. James Webb later revealed glowing edges, newborn stars, and red jets called Herbig-Haro objects. We may be seeing the pillars in their final act. A nearby supernova might already have battered them to pieces long ago. Because light takes time, that destruction hasn't reached our eyes yet. For us, the pillars still stand, frozen in a cosmic postcard. Looking outward is always looking backward. Despite their serenity, these clouds churn with motion. Gas swirls, gravity gathers, and newborn stars push back with light. It's a slow dance that sculpts structure from chaos. All of it unfolds quietly in the coldest, darkest halls of space. And every star, including our sun, began this very way. About 4.6 billion years ago, a Milky Way cloud much like this collapsed. A protostar kindled, our sun lit. The remnant disk built planets and moons. When we study the pillars, we're reading our own origin story. It's the arc of star birth, life, and seeding the galaxy with new ingredients. That's why the pillars feel so personal and so grand. They're not just cosmic artwork. They're a mirror of beginnings. Maybe that's why their image stirs something deeper than awe. Remember what you're seeing, the quiet chaos of creation at work. Light that left thousands of years ago to show us how suns begin. A place where darkness hides the engines of light. The universe is not empty or still. It is always building. Stars are born, live, die, and enrich space with the stuff of worlds. The cycle repeats, filling new nurseries with new possibilities. The story of creation isn't far away. It's written in us. Every atom we carry is a line from that script. In the silent darkness between the stars, immense clouds drift like cosmic dreams. They are nearly invisible in the black of space, cold and tenuous, but they hold the seeds of everything. Within these sprawling nebulous veils lie the basic ingredients of creation. Tiny particles of dust mingle with gas atoms, and together they form the raw material from which new stars will be born. Here in these unassuming expanses, the story of every star, even of our own sun, quietly begins. These clouds are ancient and patient. They carry hydrogen and helium, the simplest and most abundant elements in the universe, forged in the Big Bang itself. Every cubic centimetre holds only a few stray atoms on average, yet across light years, the collective mass is staggering. Hydrogen, often bonded in pairs as molecules, drifts gently in the gloom. Helium, a silent partner, floats alongside. They make up nearly all of the cloud's mass, the vast canvas on which cosmic artistry will take place. Among them is a much smaller, but crucial, presence: cosmic dust. Dust grains pepper these clouds, like fine smoke, sparse, but significant. These grains are tiny, many no larger than particles of soot or sand, but they are rich in history. They formed in the atmospheres of old, dying stars, and in the fiery aftermath of supernovae, when heavier elements coalesced into solid bits. Scattered by stellar winds and explosions, this dust became part of the great interstellar clouds. Each mote of dust carries elements like carbon, silicon, oxygen, and iron, the same elements that one day will build planets and perhaps life. They are specks of ancient stars, recycled and ready to seed new worlds. In the darkness, you cannot see this dust with your eyes, but its presence is felt. It absorbs and dims the starlight that tries to pass through the cloud, wrapping the nursery in a veil of secrecy. If you were floating nearby, you would see the surrounding stars fade to a reddish hue as their blue light is scattered and swallowed by the dust. Deep inside, visible light struggles to escape. The cloud's interior remains hidden in shadow. It is as if nature uses this dust as a curtain, ensuring that the earliest stages of creation take place in gentle secrecy, far from prying eyes. Yet not all is quiet obscurity. Though they shroud the light, the dust grains also play a creative role. They act as tiny gathering places for atoms and molecules. On their surfaces, simple gases like hydrogen can meet and join into molecules. In the extreme cold of these clouds, only a few degrees above absolute zero, dust grains also become the home of ices. Water, carbon dioxide, methane, and other simple compounds can freeze onto the dust, forming icy coatings. In this way, dust grains become chemical crucibles, bringing atoms together and knitting the first threads of complexity. Within these frigid shelters, even organic molecules can form, the building blocks of life emerging long before any star warms the scene. The scale of these clouds defies imagination. Some stretch for hundreds of light years across, great sprawling complexes of gas and dust. Others are smaller puffs, mere light years or less in size, scattered between the stars. One famous example towers in a region called the Eagle Nebula. 3 monumental columns of gas and dust, known as the pillars of creation. Each pillar is a light year or more in length, vast enough to dwarf our entire solar system many times over. They rise like ghostly towers in a celestial twilight, illuminated around their edges by the glow of nearby young stars. Inside and behind these dark pillars lie the raw ingredients of stars, gathered and waiting. The pillars of creation are iconic, but they are just one glimpse of these cosmic nurseries. Across our galaxy and beyond, countless clouds harbour similar cradles of creation. In the Orion Nebula, for instance, a massive molecular cloud blooms with clusters of newborn stars, its dust and gas lit up by their radiance. Yet even there, much of the cloud remains dark and hidden, concealing countless more infant suns still in the making. Everywhere we find these nurseries, the recipe is much the same. Abundant hydrogen, a dash of helium, a sprinkling of heavy elements and dust. These are nature's ingredients for building stars, collected over eons and spread through the galaxy. For millions of years, such a cloud can float undisturbed, a cold reservoir of potential. To human eyes, nothing obvious changes in the span of a lifetime or even a civilization. The gas drifts in a slow dance, gently tugged by distant forces, but mostly it remains in delicate balance. Inside the cloud, the temperature is incredibly low, just a handful of degrees above the coldest possible temperature, so cold that atoms hardly move. In this deep chill, pressure is feeble. Outward push is minimal, so the cloud's self-gravity, though weak, is always poised to act. It is a precarious balance between the quiet pressure of cold gas trying to expand and the ever-present pull of gravity trying to draw everything inward. Gravity is patient and persistent. Even tiny fluctuations in the cloud's density can draw its attention. Maybe in one region, by pure chance, a few more molecules gather than elsewhere. This region is ever so slightly denser, an almost imperceptible knot in the gossamer fabric of the nebula. Gravity begins to tug at this knot, pulling in more nearby gas. As the knot gains mass, its gravitational pull grows stronger, attracting yet more matter. Slowly, quietly, what was once a diffuse whisper of gas becomes a gathering pocket of material. The balance tips. Gravity's gentle hand is starting to take hold, coaxing the cloud towards collapse. Sometimes the nudge is not purely by chance. Across the galaxy, events can send ripples through these clouds, urging them to give in to gravity. The shock wave from a distant supernova explosion, the death throes of a massive star, can sweep through a cloud and compress it in passing. Or the movement of the galaxy's spiral arms, rotating like a grand pinwheel, can squeeze clouds as they orbit, like a slow-moving traffic jam of starlight and gas. Even the pressure from nearby young stars, blasting out ultraviolet light and stellar winds, can carve into a cloud's edges, herding gas into denser clumps. These external nudges are gentle on the scale of the cloud, but significant enough to disturb the delicate equilibrium. And once disturbed, gravity does the rest. Deep within the cloud, the denser regions, we can call them clumps or cores, begin to shrink under their own weight. What was cold and still starts to grow warmer at its center as gas particles fall inward and collide. In one such collapsing core, the material is gathering into a center that will one day be a star. It starts slowly. Over tens of thousands of years, the core contracts from a size larger than our solar system to something on the order of the Earth's orbit. As it does, its density soars and the central temperature climbs. The process is inexorable but graceful, like a slow inhale, drawn out over millennia. From the outside, all of this remains invisible. The collapsing core is encased in the cloud's dusty veil. To an optical telescope, there is nothing new to see. The darkness remains, perhaps growing even darker, as the core becomes denser and swallows more light. For a long time, humans could only imagine what wonders were unfolding inside. We would see dense, dark nebulae and suspect that stars were being born there. But the birthing process was hidden. It was nature's secret workshop. But human curiosity is as persistent as gravity. Over the last century, we learned to peer behind the veil using other forms of light. Infrared light, which is essentially heat radiation, can emerge from cooler, dust-shrouded places where visible light cannot. Radio waves, with their long wavelengths, pass through dust almost unimpeded, carrying messages from deep within the cloud. With these new eyes, infrared telescopes and radio antennas, we began to glimpse the hidden nurseries of stars. When astronomers first aimed infrared detectors at dark molecular clouds, the view transformed. Regions that looked like empty blackness in visible light suddenly glowed with a subtle warmth. The dust itself emits a faint infrared glow, betraying its presence and outlining the shape of the cloud. More excitingly, points of light began to appear from inside the clouds. Embryonic stars, still wrapped in their cocoons, but radiating gently in infrared. We were witnessing, for the first time, the first flickers of starlight from within the womb of the nebula. One of the most striking revelations came from the Eagle Nebula's Pillars of Creation. The Hubble Space Telescope's famous 1995 image of this region showed towering pillars of darkness against a glowing background. Beautiful, but hiding their treasures. Years later, when we observed the same pillars in infrared light, the scene changed dramatically. The pillars became ghostly and translucent. Inside and around them, dozens of previously hidden stars came into view. These newborn stars, invisible in Hubble's visible light image, now shone clearly in infrared. It was as if we had lit a candle inside a dark room, revealing forms that were always there, but unseen. With the newest generation of observatories, like the James Webb Space Telescope, our infrared eyes have grown even sharper. Webb turned its gaze to the pillars of creation and saw them in unprecedented detail. Through Webb's eyes, the pillars are not solid towers, but intricate wisps glowing at their edges. Countless red-orange orbs of light, each one a young star in its infancy, pepper the image. Some shine brightly, surrounded by diffraction spikes, marking them as brilliant sources of infrared light. These are stars that have recently formed within the pillars, now piercing through the dust with their heat and light. Along the edges of the pillars in Webb's view, a faint, eerie glow appears, almost as if the tip of each pillar were smouldering. This is not fire, but the aftermath of cosmic fireworks. Jets and shock waves from the newborn stars. When a new star forms, it often shoots out twin jets of hot gas from its poles, narrow beams blasting outwards. As these jets slam into the surrounding cloud at supersonic speeds, they heat the gas and cause it to glow. In the infrared image, those impacts trace wavy patterns of warm, excited hydrogen gas, glowing like embers, outlining the pillar's edges. It is direct evidence of active, ongoing starbirth, the hidden nursery revealed in action. Radio telescopes, too, have unlocked secrets of these clouds. When pointed at a molecular cloud, they detect the faint whispers of molecules floating in the dark. Each type of molecule emits radio waves at distinctive frequencies, like a fingerprint. By capturing these signals, astronomers have identified a rich inventory of chemistry within star-forming clouds. Simple molecules like carbon monoxide, ammonia, and water are abundant. More complex organic molecules, such as methanol, formaldehyde, and others, are also present, riding on the dust grains or free in the gas. These radio detections tell us that even before a star is born, the cloud is alive with chemical activity. In fact, some of the fundamental chemical ingredients of life are brewed in these cosmic cauldrons long before planets come to exist. Observations at radio wavelengths also let us map motion inside the clouds. The molecules aren't just sitting still, they are moving, sometimes at several kilometers per second. By studying slight shifts in the radio waves, a Doppler shift, the same effect that makes a siren change pitch as it moves, scientists can tell when gas is swirling toward or away from us. These maps revealed something surprising. Star-forming clouds are turbulent. Far from being serene, their interior gas moves in eddies and currents, churning like the atmosphere of a planet, only in slow motion and colossal scale. This turbulence plays a key role in shaping the fate of the cloud and the stars forming within it, hinting that our earlier image of quiet, gentle collapse was only part of the story. Still, even with turbulence, for a star to form, there must come a moment when collapse dominates a particular region. Inside a collapsing core, as we glimpsed, the temperature and pressure at the center begin to rise. Eventually, the infalling gas is halted, not by the cloud's overall pressure, but by something new. The pressure of the core itself becomes significant as the gas compresses tighter. The infall slows, and the dense center becomes a protostar, a very young star that has not yet begun to shine from fusion, but is glowing from the heat of its own making. This protostar is like a baby still in the womb, not yet having taken its first breath of nuclear burning, but very much alive and growing. Imagine being inside such a protostar's cocoon. There is a faint reddish glow. Dust and gas around you are warm. It's not a fierce brightness, but a gentle heat permeating the darkness. This is the light of gravitational energy being turned into warmth. As gas falls onto the forming star, it releases energy, much as a hammer hitting a surface produces heat on impact. That energy, trapped inside the thick dust, creates an infrared glow. From outside, we would see just a dim ember through the dust if we had an infrared camera, evidence that something is there, trying to shine. As the protostar grows, it gathers more mass from the infalling cloud. Most of this material doesn't fall straight in. It spirals around, forming a rotating disk of gas and dust around the protostar. This disk, the protostellar disk, is a natural consequence of the conservation of angular momentum, and it too is a crucial part of the story. Within that disk, some of the remaining dust and gas will eventually form planets, moons, and asteroids once the star fully ignites. For now, in the early stages, the disk serves as a pipeline feeding the protostar and an outlet launching the jets. The magnetic fields threading through the disk and star system can channel some of the infalling material into high-speed outflows along the star's poles. It is a dramatic paradox of star birth. Even as a star gathers itself together, it sends part of its surroundings away in violent streams. These bipolar jets burst out from the poles and can extend for light years, like cosmic fountains. They plow into the cloud, clearing out cavities in the dense gas. If we were to see this up close, we would witness colossal beams of gas, heated to thousands of degrees, carving through the darkness. They carry away not only material, but also excess angular momentum, preventing the newborn star from spinning too fast. The scene is still hidden from human eyes in visible light, but in infrared and radio wavelengths, we catch glimpses, bright knots and shock fronts, where the jets slam into the cloud, glowing as they cool. Time in these stellar nurseries flows at a different pace. What seems like a violent outburst frozen in a telescope image is, in reality, a slow, unfolding process when measured in human terms. The jets can continue to pulse for tens of thousands of years. The protostar's accretion, the feeding on surrounding gas, similarly lasts for tens to hundreds of thousands of years. All the while, the protostar is getting denser and hotter at its core. When that core temperature climbs to around 10 million degrees, a profound change occurs. Hydrogen atoms begin to fuse into helium. That is the spark of true starlight, the moment the protostar becomes a star. The onset of fusion is like the lighting of a furnace deep within the infant star. Energy from nuclear reactions floods out from the core, and the star begins to shine brilliantly. At first, much of this light is still trapped by the surrounding cocoon, but it intensifies. The balance of forces shifts. Radiation pressure from the newborn star and the stellar wind, a stream of charged particles flowing outward, start to push back against the infalling material. The cocoon of gas and dust is gradually blown away, like morning mist evaporating under the rising sun. On the outside, one day, the dark cloud that concealed the protostar is lit from within and then torn asunder. A new star's light pierces through, announcing its arrival to the cosmos. What was once an opaque, cold clump is now a glowing young star, surrounded by a thinning veil of leftover gas. If the star is massive and hot, its fierce radiation will ionize the remaining gas around it, making it glow in beautiful hues as a newborn nebula. If the star is more modest, like our Sun, it will still disperse its immediate surroundings, perhaps with help from winds or gentle radiation, until it stands free in the open. In the pillars of creation, scientists have spotted exactly this process in action. Near the tips of those dusty columns, the Hubble Space Telescope observed tiny protrusions, little bumps on the tops of the pillars that seemed to glow. These features, poetically named evaporating gaseous globules, or EGGs, are clumps of gas just beginning to be lit and eroded by emerging stars inside them. A young star within an EGG will eventually break free, its light boiling away the clump that once hid it. The pillar will lose a piece of itself each time a star is born, gradually wearing down like a sandcastle under the incoming tide of starlight. Each new star is like a torch being lit in a dark cavern. One by one, as they ignite, the nursery that was once lightless becomes filled with points of light. These stars are still young and often restless. Many will be variable, their brightness flaring as they continue to accrete material, or as their surface settles into the steady glow of maturity. Some might eject sudden flares or winds, but they are stars now, in their own right, newborns in the cosmic family. What becomes of the vast clouds that gave them birth? Over time, the formation of these stars profoundly changes their environment. A cloud that was once cold, dark, and quiescent turns into a lively, illuminated region of space. The heat and stellar winds from the newborn stars begin to disperse the remaining gas and dust. Intense radiation from the more massive of the young stars can create expanding bubbles of hot, ionized gas. These bubbles push into the surrounding cloud, sculpting it into intricate shapes, sometimes creating more pillars, ridges, or fronts, where new compressions may trigger the birth of yet more stars in a kind of chain reaction. In the Eagle Nebula, the very existence of the pillars of creation is a testament to this sculpting process. They are shaped by the influence of nearby hot stars. Just beyond the frame of those famous images lies a cluster of massive, bright stars that recently formed from the same cloud. Their radiation and winds are blasting against the cloud, eroding it. The pillars are the parts of the cloud dense enough to resist being blown away immediately. They act like cosmic windsocks, trailing away from the cluster as the fierce stellar winds eat into them. Over the next hundreds of thousands of years, those pillars will likely dissipate entirely, leaving behind just the cluster of young stars that once were born inside them. The nursery's job will be done, and the remnants of its material will be scattered into space, possibly to be incorporated into other clouds, or even into future generations of stars and planets. The scene repeats across the galaxy. Stellar nurseries do not last forever. They are transient, beautiful phases in the life of interstellar matter. After a burst of star formation, a molecular cloud may find itself largely dispersed. The stars it made, however, endure, drifting away from their birthplace. Many stars form in groups or clusters within the same cloud, so when they emerge, they form a loose star cluster. Over millions to billions of years, these clusters might spread out, with stars wandering from their siblings. Our own sun likely formed in such a cluster, side by side with many other stars that have long since migrated elsewhere in the Milky Way. It is a humbling thought that the night sky might contain stars that were born right alongside our sun, now distant strangers sharing only a common age and origin. Yet, even as one cloud fades, new clouds are forming, and others are being stirred to life by fresh events. The galaxy is ever-changing, a giant ecosystem of gas, dust, and stars. Turbulence and motion permeate it on all scales. Within star-forming clouds, as radio observations have shown, the gas moves in complex flows. Turbulence both hinders and helps star formation in a delicate balance. The internal motions prevent every last bit of a cloud from collapsing at once. They keep star formation slow and drawn out. If a cloud of 1 million solar masses collapsed altogether, it would form a burst of stars in a cosmic instant, a brilliant but short-lived fire. Instead, turbulence breaks the cloud into pieces, into filaments and clumps, dispersing some gas and concentrating other pockets. The result is that only a few % of the cloud's material actually becomes stars, even over its entire active lifetime. Nature seems to prefer a controlled burn over an explosion. Within those same turbulent flows, however, lie the seeds of new stars. The shock waves and eddies can create the dense kernels that gravity then seizes upon. It is a beautiful synergy. The chaos of turbulence sows the order of star formation. The very movement that keeps the cloud aloft also creates tiny sanctuaries where collapse can begin. In this way, the cloud gradually transforms itself, a few stars at a time. And as those stars arise, they in turn inject energy back into the cloud, through their winds, their light, and eventually their deaths, sustaining the turbulence. It is a self-regulating cycle, almost as if the cloud is alive in a sense, able to moderate its pace of turning gas into stars. Gravity, the orchestrator of collapse and turbulence, the master of disorder, work in tandem to sculpt the outcome. Magnetic fields thread through these clouds as well, subtly influencing the flows of charged gas and adding another layer of complexity. And in time, the process reaches a natural end. If the cloud runs out of sufficiently dense pockets, or if stellar feedback grows too strong, the star formation slows and stops. What remains of the gas may simply drift off, perhaps to join another nearby cloud, or to remain as diffuse interstellar medium, gently lit by starlight, but no longer forming new suns. To us, accustomed to thinking in years or centuries, these changes are essentially eternal. But on the grand timescale of the galaxy, they are happening everywhere, all the time. At this very moment, in a nebula thousands of light years away, a new star might be taking its first breath of fusion fire, pushing away its cradle. In another cloud, a shock from some long-ago supernova might just now be compressing gas enough to spark a collapse that will, after many ages, result in a shining star. The Milky Way is sprinkled with regions at every stage, from cold quiescent clouds on the verge of awakening to hot star-forming cauldrons glowing with the energy of hundreds of young stars, to dispersed ashes of clouds that already gave their light to the galaxy. This continuous cycle of birth, radiation, and dispersal drives the evolution of galaxies. Without it, galaxies would be dark, static places. Instead, they are vibrant and ever-renewing. Each generation of stars enriches the galaxy further with heavy elements. When the most massive of these newborn stars live out their brief lives and explode, they scatter elements like carbon, oxygen, iron, the stuff of planets and life, into space. Those elements mix into the next generation of clouds, which will form the next generation of stars. In this way, each star-forming nebula is not just a nursery, but also a repository of the past, containing atoms from countless earlier stars, now recombined into new structures. The pillars of creation and similar nurseries illustrate a chapter of this story, but the story itself spans the entire universe. There is something deeply reassuring in the thought that the cosmos continually regenerates its most luminous components. Even as old stars die, new stars are born. The places where this happens are tucked away in hazy nebulae, often out of sight. But we know they are there. All it takes is a patient gaze in the right kind of light to witness them. As our understanding grows, we also find that star formation is not a uniform process, but comes in many flavors. Some stars form alone or in pairs, others in rich clusters. Some form quietly, deep within small, isolated globules, while others emerge amid hundreds of siblings in a massive cloud. The basic ingredients and rules are the same, but the outcomes vary in detail. It's a bit like baking with the same ingredients, but getting different breads and cakes. Environment and conditions matter. A small cloud might create a few low-mass stars that gently shine for billions of years. A massive cloud might forge dozens of huge stars that blaze hot and blue, only to detonate as supernovae after a short lifetime, triggering new clouds nearby as they do. And so the dance continues, standing back. If we could watch a time-lapse of 1,000,000 years in one of these star-forming regions, we would see the cloud churn and fragment. We'd see pockets glow, then burst into radiance as stars ignite. We'd see bubbles inflate around those newborn stars, pushing the gas into new shapes. Filaments of dust and gas would waver, twist, and dissipate. In the end, much of the cloud would dissolve away, and a cluster of stars, bright, newborn suns of various sizes, would remain where once there was only darkness. Eventually those stars would wander off, and the area would fall silent, until perhaps much later a new cloud drifts in to start the cycle anew. For now, we are catching only snapshots of this immense process. Each observation, each telescope image, is a frozen moment in a story that spans eons. Yet from those moments, we piece together the narrative. We infer what must have come before and what will happen after. In the Pillars of Creation snapshot, we see active star formation, and can imagine that before those pillars stood tall, the area was just a larger cloud. We can foresee that in time the pillars will be eroded away. In Orion's glowing nebula, we see a mid-stage nursery. Already a cluster has formed and cleared some of the cloud, but new stars are still being born at its edges. In darker clouds like the coal sack near the Southern Cross, nothing yet shines inside. It might be a future nursery, or perhaps quietly incubating its first stars unannounced. The universe moves to the rhythm of these births and deaths. Here in these nurseries, the tempo is slow, measured in millennia, but inexorable. There is a quiet inevitability to a cloud rich in gas and dust. Given time, it will form stars, and those stars will change the scene entirely. It's as if nature sketches a delicate draft in gas, then slowly pulls the ink of gravity across it to draw in the lines, then finally sets it ablaze with starlight and clears the page for the next drawing. Drifting in a cosmic cloud, you would feel nothing of this. The gas around you would be almost a vacuum by earthly standards. You might not even realize you were in a cloud until you looked back to the stars behind and saw their light muted. It's a realm where the grandest of events originate from the most imperceptible beginnings. A slight whisper of denser air, a subtle convergence of floating particles. That is all it takes to begin a cascade that ends with the brilliance of a star. In that sense, gravity's hand truly is gentle. It works with the barest of hints, the faintest seeds, and amplifies them into great balls of fire. As we conclude our journey through these pillars and clouds, we carry a new appreciation for the darkness between the stars. No longer do we see it as empty or void. We know now that it is full of promise and process. In those inky regions are the cradles of light, quietly gathering the next generation of suns. Every twinkling star in the night sky was once an invisible embryo in such a cloud, nurtured in darkness, until it could stand on its own and shine. The cosmos has many such cradles at this very moment, and each is a beacon of creation in progress. From the raw ingredients of hydrogen, helium, and dust, to the gentle pull of gravity assembling them, to our modern eyes peering into the hidden nurseries, to the first light of newborn stars piercing the dark. We have traced the arc of creation's beginning. We have seen that the birth of stars is not a sudden spark, but a slow, wondrous unfolding. It is a tale of contrasts. Darkness giving way to light, chaos giving birth to order, gentle forces triggering great luminosity. It reminds us that even in stillness, there can be profound change brewing just out of sight. And yet, this is just the opening chapter in the life of a star. The young stars that emerge will go on to live out lives that we have yet to explore. Those lives will take them from their nursery into the wider galaxy, where they will burn for millions or billions of years, perhaps foster planets around them, and eventually transform again when their own fuel is spent. The journey that begins in the quiet pillars of creation will continue, branching into new stories of starlight, planetary birth, and cosmic evolution. For now, we leave the tranquil nursery with its soft cosmic glow, knowing that within it, new stars are waking. They will soon light up the universe in their own time. As we gently drift away from the Eagle Nebula and all the hidden cradles like it, we remain in awe of what we have witnessed, the sight of the pillars of creation, standing silently against the starry expanse, will stay with us, a reminder of where we all come from. These are the places where stars are born, and in their light we find our cosmic origins. The story continues, carried on the beams of starlight that will travel across space and time, inviting us to follow, to learn, and to wonder at what comes next. Now our cosmic journey carries us out across thousands of light years to a new and wondrous realm. We are drawn toward a faint, distant glow in the constellation Serpens. At first, it appears as little more than a hazy patch against the darkness, barely visible to the naked eye from Earth. But within that subtle shimmer lies one of the galaxy's great nurseries of stars, a place shrouded in mystery and promise. It is the Eagle Nebula, an enormous cloud of glowing gas and dust, alive with the process of creation. As we venture closer, the faint haze blossoms into a rich tapestry of light and shadow. Spread out across dozens of light years, the Eagle Nebula reveals itself as a glowing veil draped against the starry background. Its gas is excited to a gentle fluorescence by the energy of young stars embedded within, giving the nebula a soft, ethereal glow. Dark patches of cosmic dust wind through the cloud like wisps of smoke, obscuring and revealing different parts of this celestial scene. The closer we drift, the more detail emerges in this vast interstellar cloud. Scattered across the nebula are the brilliant lights of a newborn star cluster. These infant suns, only 1 million or 2 years old, shine hot and bright in the heart of the Eagle Nebula. Their combined radiance lights up the surrounding gas, carving out a hollow in the nebula's center where the cluster resides. From afar, this cluster's glow is what first announced the nebula's presence to astronomers centuries ago. Through early telescopes, observers noted a faint starry patch surrounded by haze, a subtle clue that something remarkable lay hidden there. In the 18th century, an astronomer peered through his telescope at this very region and recorded a smudge of light in Serpens. Little could he imagine what modern eyes would later uncover. As we float here now with the power of present knowledge, we see not a mere smudge, but a sprawling nebula teeming with structures and activity. Over time, stargazers gave this cloud poetic names inspired by its shape. Some saw the form of an eagle with outstretched wings, earning it the name Eagle Nebula. Others fancied the silhouette of a regal figure amid the stars, calling it the Star Queen Nebula. Both names hint at the dramatic shapes etched into the darkness and at the secrets awaiting within. We find ourselves approaching the nebula's central region, where the light of the young cluster meets a particularly dense curtain of darkness. It is as if a great veil hangs within the nebula, partly hiding what lies beyond. Here, swirling clouds of dust form a mottled screen that blocks the bright glare of stars behind it. This is the Eagle's veil, a tapestry of interstellar dust and gas that both conceals and reveals. We see it illuminated around the edges by starlight, yet opaque at its core. Drifting deeper in, we sense that something monumental looms just behind this veil. Then, slowly, they come into view. 3 towering forms materializing out of the twilight of the nebula. At first they are just silhouettes against the glowing backdrop, elongated shadows stretching upward. As our eyes adjust, these shadows resolve into colossal structures of gas and dust, rising like pillars from a cosmic cloudscape. They stand side by side, reaching into the luminous void, majestic and still. We have arrived at the heart of the Eagle Nebula's mystery, the very home of new stars. Emerging from behind the veil, the pillars of creation rise before us in silent grandeur. These pillars are vast, monolithic clouds, sculpted by cosmic forces. Each pillar is a column composed primarily of cool molecular hydrogen gas, mingled with darker dust grains, the raw material for new stars. Shaped into long, finger-like forms, they tower for several light years from base to tip. We can scarcely comprehend their scale. One pillar alone stretches across trillions upon trillions of kilometers. In fact, if a single pillar were transplanted to our solar system, it would dwarf it, extending far beyond Pluto's orbit and enveloping everything in between. These structures are so immense that from end to end, each one spans a distance that light itself takes years to travel. Up close, the pillars exhibit rich hues and intricate patterns. In visible light, they appear in shades of deep umber and reddish brown, tinted by the dust that absorbs and reddens starlight. Their surfaces are uneven, marked by clumps and filaments of material clinging together. These denser patches are enough to cast shadows within the pillar's own form. The long columns with rounded heads have earned the nickname elephant trunks, as their shapes evoke the image of enormous elephants raising their trunks skyward. Indeed, they resemble the trunks of celestial elephants, lifting their heads toward the heavens, or perhaps giant stalagmites rising from the floor of a cosmic cavern. Against the glowing curtain of the nebula, the pillars stand out as dark silhouettes outlined by light. They are dense enough to block the brilliant backdrop of stars and glowing gas, appearing almost black in contrast. Yet along their edges, facing the star cluster, a soft radiance outlines their contours. It is as if three monumental towers stand before a cosmic sunrise, their ridges gilded by the dawn. Here, that sunrise is the fierce, ultraviolet light pouring out from the hot young stars nearby. The side of each pillar, facing those stars, is aglow, illuminated by energetic starlight, while the opposite side remains in deep shadow. This stark interplay of light and darkness gives the pillars a striking, sculpted appearance, highlighting their every curve and protuberance. Upon the pillar's upper reaches, we notice peculiar finger-like protrusions jutting outward. These small bumps at the tops of the columns are actually silhouetted clumps of gas so dense that they manage to resist the onslaught of radiation longer than their surroundings. Astronomers call them evaporating gaseous globules, or EGGs, an appropriate name, as within these cosmic eggs, new stars are gestating. Each EGG acts like a shield, blocking the intense ultraviolet glare behind it and casting a long, tapered shadow directly beneath it. This is why the pillars have that ragged, fingered look at their tops. The EGGs protect the gas immediately below, allowing a thin trail of cloud to survive in their shadow, while everything around is boiled away. Inside some of these dark EGGs, protostars, baby stars, are taking shape, quietly growing until one day they will ignite and burst forth with their own light. Occasionally, a newborn star within the pillars makes its presence known, even before it fully emerges. With sensitive vision, one might catch a faint glow or a narrow beam of energized gas shooting out from the column, signifying a young star announcing its birth. In fact, scientists have observed at least one such jet, a slender outflow from a nascent star hidden in the leftmost pillar. It pierces through the surrounding gas and dust like a tiny beacon. a herald of the new star's presence. These stellar jets are fleeting signs, but they tell us that inside these dusty towers, stars are actively forming and starting to influence their environment. For a long time, much of this fantastical scene remained hidden to human eyes. The thick dust rendered the pillars almost impenetrable in visible light, concealing the stars forming within and beyond. But when we peer with infrared eyes, the view transforms. In infrared light, which can pass through dust more easily, the pillars become translucent. What was once an opaque wall now reveals countless stars peppered throughout and behind the columns. In recent years, the James Webb Space Telescope turned its gaze on this region, capturing the pillars in stunning infrared clarity. Suddenly, the dark columns appear as gauzy, glowing outlines, and a tapestry of countless previously hidden stars fills the scene. It is as if the pillars shed their secrecy under infrared vision, allowing us a glimpse at all the young suns scattered inside this stellar nursery. Even the far side of the nebula, beyond the pillars, comes alive with distant starlight. This duality of views, opaque in visible light, yet nearly transparent in infrared, reminds us that there is always more to reality than what our eyes alone can see. The forces at work here are as awe-inspiring as the structures themselves. The brilliant cluster of young stars near the pillars is not a quiet neighbour. It bombards the region with intense radiation and powerful stellar winds. These winds, streams of charged particles flowing at incredible speeds, slam into the pillars' surfaces, much like a constant gale against a cliff face. Over time, the relentless battering by both ultraviolet radiation and fast winds has sculpted the pillars into their present forms. They effectively act like cosmic sandblasting tools, stripping away gas and dust from wherever it is less dense, and leaving behind only the more resilient, compact parts of the cloud. The three pillars we see are, in a sense, the remnants of a once larger cloud structure. They stand where the material was thick enough to hold out against the erosion, while the surroundings were whittled away by the star's energetic outflow. Perhaps long ago, this region looked very different. One can imagine a vast blanket of gas and dust that stretched across space here, before any stars had formed to disturb it. Then came the first generation of young, massive stars in the cluster. When those stars turned on, their radiation and winds began to push into the cloud, carving out cavities and hollowing the nebula from within. In areas where the cloud was tenuous, the material dispersed quickly. But in parts that were denser, the parts that became the pillars, the erosion was slower. Each dense clump shielded gas lying just behind it from the brunt of the stellar winds, creating a pillar-like extension of shadowed material. Bit by bit, what started as small bumps grew into elongated towers as the space around them cleared away. The iconic shape of the pillars of creation was born from this battle between stars and cloud. It is an exquisite structure created by destruction, sculpted by the very forces that will eventually dismantle it. Change is the norm in such cosmic landscapes, though it unfolds on timescales far beyond human perception. Even now, the pillars are slowly evaporating under the assault of starlight. Every year, they shed mass as gas is boiled off their surfaces and dust is flung outward into space. Astronomers studying images of the pillars, taken decades apart, have discerned subtle hints of this progress. Small streamers of gas being carried off, the delicate edges retreating imperceptibly. In our short lives, we cannot see them visibly change, but given millennia, the transformation would be dramatic. The pillars would gradually shrink and wither away, losing their defined shapes as the stars relentlessly chip at them. They truly are a living sculpture, constantly being reshaped by their environment. There is also violence lurking on the grander scales of time. From time to time, massive stars meet explosive ends as supernovae. Such an event near the Eagle Nebula could send a shockwave tearing through these clouds. Indeed, some evidence suggests that thousands of years ago, a titanic stellar explosion occurred in this vicinity. The shockwave from that blast would have swept through the Eagle Nebula, potentially toppling structures like the pillars in a swift, devastating blow. If so, the pillars of creation might have been shattered long ago by an invisible cosmic storm. Yet, as of now, they still grace our skies, unchanged in our eyes, a sign that if the destruction happened, its aftermath has not yet reached us. The nebula is thus both creative and destructive, a place where new stars are born, even as their birthplace is eroded away. This interplay of death and rebirth is the very essence of a star-forming region. From the destruction of the cloud, new stars emerge, and those stars in time will likely sow the seeds of future creation. The dust and gas being blown off the pillars will mix into the wider nebula, potentially collecting elsewhere to form new dense clumps, perhaps new pillars, or even future planets around those young stars. Meanwhile, within the pillars, the protostars growing there represent the next generation. When they eventually ignite fully and the shrouds of dust fall away, those stars will illuminate the scene anew. They may even carve out smaller pillars around them as they begin to shape their own surroundings. In this way, the cycle of star formation continues in the nebula. Over millions of years, the Eagle Nebula will not look the same as it does now. The pillars we admire today will likely be gone in a few million years, dissolved into stardust. But by then, the young stars born here will have matured and drifted away, and some will have exploded in turn, creating fresh nebulae elsewhere. In that sense, the Eagle Nebula is a temporary artwork, a snapshot of one stage in the never-ending cycle of stellar life. It is a living sculpture, slowly changing form while it creates living suns that carry forth its legacy. And though the pillars will vanish in time, the stars they leave behind will continue the story, perhaps lighting up new clouds in some far future, starting the process anew. As we observe the pillars of creation from our vantage point, we are not only looking across space, but also back in time. The nebula lies around 7,000 light-years from Earth, so the light we see today set out on its journey long before human civilization had even begun to record history. We are witnessing the Eagle Nebula as it was millennia ago. In the interim, untold changes may have occurred there without our knowledge. This fact lends an extra layer of wonder and poignancy to the view. It is like seeing a preserved instant of cosmic history, frozen in the sky for us to study. One intriguing implication of this light travel time is that the current fate of the pillars of creation could be different from their appearance. In the mid-2000s, astronomers using a space telescope detected a strange cloud of hot dust near the pillars. They speculated it might be the aftermath of a supernova, possibly the very explosion whose shockwave could have obliterated the pillars around 6,000 years ago. If so, a catastrophic fate may have overtaken the pillars without our knowledge. If that is true, then the majestic structures we now behold no longer exist as we see them. They would have been dispersed into space, their dust and gas blown apart by a stellar cataclysm. However, because their demise would only become visible after the light carrying that news arrives here, the pillars would continue to adorn our sky for centuries to come. They would linger like ghosts, visible only by the ancient light still travelling towards Earth. Whether the pillars have already been destroyed by that distant supernova or not remains a mystery. Later observations have cast doubt, finding no definitive blast remnants in the area, which suggests that perhaps the pillars are still standing, slowly eroding, rather than having been instantly demolished. For now, the pillars of creation still rise in our telescopes, looking much as they did when first photographed decades ago. But the uncertainty adds to their mystique. We are witnessing a celestial spectacle that might already be gone, or might yet persist for a long time to come. We are reminded that in astronomy, we are always a bit behind the present, peering into the past and wondering about the present, unseen. As we prepare to drift onward, we carry with us the image of these distant pillars and the lessons they embody. They have shown us how dramatic and beautiful the birthplaces of stars can be, and how transient even colossal structures are in the face of cosmic forces. The pillars of creation stand as a symbol of beginnings, the start of stars, the dawn of new light, and yet also symbolize how every beginning exists within an ending, as the clouds that cradle new stars are destined to fade. Our journey through the cosmos will continue, unveiling more wonders and deeper truths about the universe's grand design. With the glow of the Eagle Nebula at our back, we venture forward, eager to discover what other marvels await in the saga of creation among the stars. From the silent depths of a cold cosmic cloud, darkness and stillness prevail. This immense nebula of gas and dust stretches for light years, a faint shadow in the galaxy's spiral arm. Tiny motes of dust and wisps of gas hang suspended in a delicate balance. The cloud's material is mostly hydrogen, laced with trace molecules and microscopic grains of ice and carbon. These dust motes are ancient, forged in previous generations of stars and supernovae long ago. They carry heavier elements like carbon, silicon, and iron, the raw materials that will one day form planets and perhaps life. From afar, such a cloud appears as a dark blot against the starry sky, its dust blocking the light beyond. Inside, temperatures are so low, only a few degrees above absolute zero, that motion slows to a crawl. Gravity's subtle pull is gently gathering the material inward. For now, an uneasy equilibrium holds this cloud in check, and it slumbers as a cold, diffuse mass biding its time. All of this unfolds in profound silence. No sound can carry through the vacuum of space, so the birth of a star is a silent ballet, a drama of light and gravity performed in utter stillness. In time, fate intervenes with a gentle, inexorable push. Perhaps a distant supernova's shockwave sweeps through the nebula, a ripple of energy racing across light years. Or maybe the gravity of a passing star brushes the cloud, jostling it from serenity. Even the intense radiation from nearby massive stars could send a pressure wave into the cloud's depths. Any such disturbance is enough to upset the delicate balance. Gravity seizes the advantage, and the quiet cloud begins to collapse inward under its own weight. Slowly, almost imperceptibly, what was once motionless gas starts to drift and fall toward the cloud's center. The collapse, at first gentle, soon accelerates as gravity draws in more and more mass. What begins as a slow inward drift becomes a headlong rush, a cascade of gas spiraling toward an increasingly dense center. Like water swirling down a cosmic drain, the infalling material picks up speed. As it falls inward, it compresses and heats up, converting the energy of motion into warmth. The temperature in the core, once near absolute zero, climbs into the thousands of degrees. A compact center is taking shape at the heart of the cloud, growing denser and hotter with each passing moment. The great cloud is far from uniform, and under gravity's influence, it begins to fragment. Regions of slightly higher density collapse faster, breaking the cloud into pieces. Multiple dense knots of gas split off, each destined to become a new star in time. Like seeds scattered in a cosmic garden, dozens of embryonic stellar cores take shape within the larger nebula. Some fragments are heftier than others, a hint that some stars will be large and luminous, while many will be smaller and fainter. There are far more of the small clumps than the big ones, meaning this cloud will mostly birth modest stars and only a few rare giants. In one such fragment, deep at its center, a nascent protostar is forming, gathering mass and growing hotter as it contracts. It's important to remember that all of these changes occur on almost unimaginably long timescales. Nothing in this cosmic drama happens in an instant. To an outside observer peering at the nebula, centuries might pass with only subtle shifts. The collapse of a cloud, the formation of a protostar. These unfold over tens of thousands to millions of years. In our story, we fast forward through epochs to see the progression clearly. What seems like a dramatic, quick sequence is in reality a slow-motion ballet of gravity and time. Only by compressing the timeline can we truly appreciate the majesty of a star's birth. At the center of one collapsing fragment, the gas compresses into a tighter and tighter sphere. Over tens of thousands of years, the young protostar's core grows denser with each passing millennium, and its temperature steadily climbs. What was once a cold, diffuse pocket of gas is transforming into a blazing kernel of energy. The material is squeezed so tightly that its density soars. Space that once held only wisps of gas now contains mass packed shoulder to shoulder. Deep inside, the pressure becomes enormous as the weight of infalling layers presses inward. The temperature in this embryonic core leaps higher and higher, pushing toward the extraordinary heat needed to spark a star's fire. Yet for all this growing heat, the infant star remains swaddled in its birth cloud. It is like a candle flickering deep inside a foggy lantern. Its glow is muffled and hidden. Thick veils of dust and gas still surround the protostar, insulating it from the outside universe. Any light it emits in the visible spectrum is immediately absorbed by the cocoon of dust. The dust grains then re-radiate that energy as a faint infrared warmth. To human eyes, there is nothing yet to see here, just an inky darkness where a star is forming. Only in the infrared spectrum might a soft glow betray the presence of this growing ember inside the nebula. If we could venture inside this shrouded cocoon, the sight would be otherworldly. The dust around the protostar would glow with a dim reddish hue, gently lit by the warming object at its core. There would be no clear star visible, only an eerie, diffuse light filtering through swirling clouds of particles. The inner region would be hot and dense, a churning chaos of gas illuminated from within. It would feel like standing inside a glowing ember. Diffuse, ruddy light all around, and deep at the center, the embryonic star contracting and heating in silence. In this insulated world, not a single pinpoint of starlight escapes. Yet the promise of a brilliant sun is growing just beyond vision. Meanwhile, the protostar continues to contract under gravity, and its core grows ever hotter and denser. Millions of years have now passed since the collapse began, and the moment of transformation draws near. Deep within, the temperature surges into the millions of degrees. When the core reaches roughly 10 million degrees, a critical threshold will be crossed. The hydrogen atoms, which have been squeezed closer and made to move at incredible speeds, are on the verge of a profound interaction. Normally, these atoms repel one another, but in this extreme heat and pressure, they begin to overcome that resistance. A moment approaches when these atomic nuclei will collide and fuse, heralding a fundamental change, the birth of true starlight. At last, the long-awaited spark ignites quietly in the darkness. Deep in the protostar's core, hydrogen nuclei begin to fuse into helium. There is no violent blast to mark the occasion, just a steady and self-sustaining burn that lights at the center. In that instant, a new kind of fire is born. Nuclear fusion, the source of a star's light and heat. Like a match struck in the void, a steady flame takes hold that will burn for millions or even billions of years. In each fusion reaction, a tiny bit of matter turns into pure energy, unleashing a brilliant outpouring of radiation. The protostar has now become a true star, releasing energy from its core rather than merely warming by contraction. This is the moment of birth. A star is born, and for the first time, it shines with its own power. A faint but persistent glow kindles at its center, the newborn star's first true light. From the cold dust and silence, a star's internal fire has been born. Deep within the collapsing cloud, what was once mere darkness now glows with stellar light. A new star quietly kindles, hidden in its cocoon, marking the successful transformation from dust to flame. Now the newborn star finds itself in a delicate balancing act. The tremendous energy pouring from the core pushes outward, creating pressure that resists gravity's inward pull. Deep inside, countless particles of light and searing gas rush upward, straining to expand the star. At the same time, gravity continues to tug downward on every layer, trying to draw all the gas back in. Where once gravity was driving an unchecked collapse, it is now met by an equal opposing force from within. The star's contraction slows, then finally halts. It is as if the star has taken a deep breath and paused. A gentle equilibrium settles in, a fragile peace between gravity's squeeze and the outward push of heat and light. This harmonious state is known as hydrostatic equilibrium, a cosmic truce between pressure and gravity. The star, no longer contracting uncontrollably, settles into a stable shape and size. It has effectively reached the main sequence of its life, the long middle age of a star's journey. Here it will spend the bulk of its years, steadily burning hydrogen in its core and shining without major change. In human terms, the star has left its turbulent youth and entered a stable adulthood. The inward crush of gravity is perfectly balanced by the outward push of the star's own heat and light, moment by moment. As if suspended between gravity and radiance, the newborn star finds a calm stability after the tumult of its birth. Though delicate, this balance is remarkably self-regulating. If the core's furnace burns a bit too fiercely and energy output increases, the star responds by swelling slightly. As it expands, its gases cool and the fusion rate eases, preventing the star from blowing itself apart. Conversely, if the core's energy production dips too low, the star contracts under gravity's unrelenting pull. That contraction heats the core up once more, stoking the fusion furnace back to a steady level. In this way, the star behaves like a natural thermostat, keeping itself in equilibrium. The result is a steady, tranquil glow, a star that can shine reliably for millions or even billions of years, its inner peace maintained by this balance. The newborn star now shines steadily, having secured its fragile peace. Its inward collapse has been halted, and it holds itself together in a tranquil poise. In the darkness of space, this young sun maintains a delicate balance, quietly burning and stable after the storms of its birth. Even as the newborn star stabilizes, the aftermath of its birth surrounds it. Not all of the infalling material made it into the star. Much of the gas and dust remains in orbit around it. The conservation of cosmic momentum has formed a broad, flattened disk encircling the young star. This protoplanetary disk is like a vast, swirling ring of debris, a cosmic whirlpool left over from the star's formation. Within this disk lies the potential for an entirely new chapter of creation. The protoplanetary disk stretches far from the star, a wide and thin expanse of material. Near the newborn star, the disk's gas is searingly hot and bathed in the star's radiance. Farther out in the disk, temperatures drop, and tiny ice crystals form on dust grains. In these distant reaches, water vapor freezes onto particles, along with carbon-rich molecules, creating a reservoir of ices that will later seed new worlds with oceans and atmospheres. All of it orbits in a flat plane like a cosmic record, turning in calm circles around the central star. Within this disk, countless particles of dust and gas jostle and drift, carrying on the legacy of the cloud that formed the star. If one could observe this scene from a nearby vantage point, the view would be breathtaking. Edge on, the protoplanetary disk would appear as a thin, dark band, bisecting the star's faint glow, with a hazy halo of scattered light around its edges. From high above, the disk would spread out like a vast, dusky carousel around a central light. Near the center, one would see a bright, warm region where the star's radiation illuminates the inner disk. Farther out, the disk would fade into darkness, lit only faintly by the distant sun at its core. It is a majestic sight, a great cosmic wheel of gas and dust, turning slowly and quietly in the void, hinting at the planets that are coalescing within. Amid this spinning disk, new possibilities emerge. Tiny dust grains begin to cling together when they collide gently, merging into larger motes. In the microgravity of the disk, particles move slowly enough to stick, helped by static electric charges and the icy, organic coatings that make them slightly sticky. What starts as fine powder coagulates into grittier clumps. Over time, countless such specks grow into pebbles, and pebbles aggregate into rocks. Millions of these small building blocks share the disk, bumping and coalescing whenever chance brings them together. Slowly, imperceptibly, the seeds of future planets take shape in the quiet, circling debris. As these clumps of matter grow, their own gravity begins to take hold. A pebble that becomes a boulder can start to tug at smaller grains, pulling them in and accelerating its growth. Before long, there are countless nascent worlds, planetesimals, orbiting the star, each one like a tiny moon or asteroid. They sweep through the disk, gathering more material in their path. In some regions, several large bodies form, and their gravitational dances tug them closer together. They might collide and merge into still larger protoplanets, or fling smaller fragments aside. It is a slow, complex ballet of creation, as pieces of dust assemble into what may one day be full-fledged planets, moons, or belts of asteroids. Over time, this once uniform disk develops structure. As nascent planets orbit and grow, they begin to sculpt their surroundings. A young planet clears a path along its orbit, sweeping up or scattering the debris there with its gravity. The result is that the disk forms concentric rings and gaps, broad bands of dust separated by narrow zones of emptiness. These structures resemble enormous versions of the rings around Saturn, except on a scale millions of times larger, and composed of gas and fine dust. Such graceful rings are like footprints in the disk, marking where new planets are being born and carving out their celestial pathways. Remarkably, we have even caught glimpses of such structures in reality. Powerful telescopes have peered at young star systems and seen the telltale rings and gaps in their disks. In distant stellar nurseries, we can observe light shining through cleared lanes, confirming that new planets are carving out spaces around their infant suns. What was once theoretical has become visible evidence of nature's planet-making in progress. These observations echo the story unfolding in our young star's disk, showing that the cosmos is dotted with other newborn solar systems taking shape. In time, on the order of a few million years, the protoplanetary disk itself will begin to disperse. The central star's intense light and winds will blow away much of the remaining gas. Dust that has not formed planets may be gradually pushed outward by starlight or drawn inward to fall onto the star. Eventually, the young star is left surrounded only by whatever planets, asteroids, and comets have managed to form in the disk's brief lifetime. The cosmic construction site is swept clean. Our own sun once had such a disk, and from it emerged the Earth and all the worlds of our solar system. A reminder that our planet's story began in a similar cosmic whirlpool of dust. Now, a young planetary system is taking shape around the star. The chaos of the disk is settling. Much of the dust has coalesced or been swept away. In the quiet that follows, newly formed planets and remnants of the disk circle their sun. What began as a cloud has not only produced a star, but also the seeds of worlds that will accompany it on its journey. It is awe-inspiring to realize that we are witnessing the formation of a future solar system. In the midst of cosmic dust and gas, new worlds are assembling, silent for now, but destined to spin around their sun for ages to come. While planets quietly coalesce in the disk, the young star is not entirely serene. In fact, newborn stars are often restless and energetic. The same processes that build planets can also send material careening away from the star. Strong stellar winds stream outward from the star's surface in all directions. A powerful flood of particles and energy, far stronger than the mild breeze our sun emits today. Even more striking are the narrow jets of gas that erupt from the star's polar regions, shooting straight out above and below the disk. These dramatic outflows are a hallmark of stellar youth, carving their presence into the surrounding nebula and announcing that a star is still in its infancy. The young star refuses to remain quiet. It vents its newfound energy in dramatic fashion, announcing its presence to the cosmos. From the poles of the young star, twin jets of gas are violently launched into space. Guided by the star's magnetic fields and rapid rotation, streams of ionized gas are flung outward at tremendous speeds, hundreds of kilometers per second or more. Each jet is like a cosmic laser beam, narrow, focused, and stretching for light years into the surrounding cloud. As these jets slam into the colder gas of the nebula, they create brilliant shock fronts that glow in vivid hues. The colliding gases emit light in a variety of colors, painting the darkness with wisps of red and blue-green. These glowing tendrils, known to astronomers as Herbig-Haro objects, mark the spots where the star's outflows crash into the interstellar medium. These outflows serve important purposes in the star's development. By ejecting matter, the star sheds some of the excess angular momentum it inherited from the spinning cloud. Without this break, The newborn star would spin ever faster as it contracted, potentially tearing itself apart. In essence, the jets and winds act as safety valves, preventing the star from rotating too rapidly or accreting too much material too quickly. It's akin to a spinning skater extending their arms to slow the spin. The star flings some mass outward and slows its rotation to a sustainable rate. At the same time, the outflows plow through the surrounding cloud, carving clear tunnels through the gas and dust. Like celestial snowplows, they push aside the leftover debris of formation. In doing so, the star gradually clears away the remnants of its birth cocoon, allowing its light to reach farther into space. For now, these magnificent jets announce to the cosmos that a star is in its infancy. But they will not last forever. Over the course of only a few tens of thousands of years, a mere blink in the star's long life, the eruptions of gas will begin to subside. As the star exhausts the supply of easily accreted material and its rotation slows, the need for such dramatic outflows diminishes. The star's surrounding disk grows thinner and more tranquil. The once violent youth of the star gradually gives way to a calmer adulthood. The blazing jets wane and finally cease, and the young star transitions to a quieter phase. It remains luminous and warm, but now without the fierce, sculpting streams that characterized its birth. The most tumultuous growing pains subside, leaving behind a star that has both shed and shaped its surroundings. Thus, the newborn star's most turbulent phase draws to a close. Its outbursts have carved out a clear space around it and released the pent-up energy of formation. The once fierce jets subside, and the star stands calmer in the void it has created. The infant star's tantrums have passed, leaving it glowing quietly in the dispersing mist of its birth. Yet this young star's story is only one among many. Inside the original giant cloud, numerous other dense clumps have been undergoing their own collapse. Stars are rarely born in isolation. They emerge in groups, siblings sharing the same cosmic nursery. All these newborn stars are of similar age and origin, forming a true stellar family born from the same nebula. As our star ignited, so too have others across the nebula, each one a bright newborn, hidden in its own cocoon. Together they form a cluster of infant stars, nestled within the remnants of the cloud that gave them life. This star is not alone in its origins. All around it, others are waking to life from the same cloud, forming a community of young suns. This newborn cluster is a community of stars of all sizes. Some of the siblings are far more massive than our star. These giant newborns blaze with brilliant blue-white light and pour out fierce, ultraviolet radiation. Their energy floods the nebula, causing the surrounding gas to glow in ethereal colors. By contrast, a star of moderate mass, like our own young sun, glows with a steadier, gentler light. It cannot match the blinding brilliance of the cluster's titans, but it will endure long after those giants exhaust their fuel. The bright, massive stars dominate the cluster's early life, their powerful stellar winds and light beginning to sculpt and disperse the remaining clouds around the cluster. Amid these luminous giants are countless smaller stars, some much tinier than our sun. These faint newborns shine with a soft red or orange light. A few may be so low in mass that they never ignite hydrogen at all. Failed stars, known as brown dwarfs, fainter than true stars, but still warm embers in the cluster. In the rich tapestry of the cluster, there are stars of every color and brightness, each contributing to the stellar family's gentle radiance. Not every fragment will manage to become a true star. In a quiet corner of the cluster, one smaller clump has been slowly contracting just like the others. But its mass is too little. Its core struggles to reach the fusion ignition point and never quite succeeds. This is a failed star, a brown dwarf, destined to glow only faintly with leftover heat. It shines a deep red, barely brighter than the original cloud, and will gradually cool over eons. This small object will drift through the cluster, an almost star that never ignited, a silent reminder of how critical the amount of mass can be in the making of a star. In their first few million years, the sibling stars huddle relatively close, shining together through the thinning fog of their nursery. Within this cluster, distances between stars can be just a fraction of a light year, much closer than the Sun is to its nearest stellar neighbours. On occasion, two young stars might drift near each other, their gravity briefly entwining. Such close passes can disturb the star's disks, stirring up cometary material or flinging nascent planets into new orbits. But mostly, the stars simply move in a slow swarm, each tracing its path within the group. If one were floating in the midst of this newborn cluster, the heavens would look very different from the night sky we know. Instead of a single sun dominating a daytime sky, many young suns would surround you on all sides. Some would burn bright blue-white, others golden or red, each a brilliant point scattered through the nebular glow. The nearest stars might be just a few light months away, so close that they would outshine the familiar constellations we see from Earth. The sky would never be truly dark. Everywhere, a star's light would cast subtle shadows. It would be a sky crowded with suns, a celestial gathering of brilliant lights sharing one cosmic neighborhood. As the cluster grows older, it often cannot hold itself together. The same stellar winds and radiation that cleared the gas also remove the gravitational glue that held the group tight. With most of the nebula gone, each star feels only the weak tug of its siblings' gravity. Slowly, the stars begin to wander. The cluster that was once a dense family drifts into a looser collection. Over millions of years, it will expand and eventually disperse entirely, its members scattering across the galaxy. Our own sun likely drifted away from its birth siblings in this manner eons ago. On rare occasions, a cluster is born so rich and tightly bound that it remains together for a long time. The Pleiades, for example, a glittering group of blue stars visible on a clear night, are sisters that have stayed together for around 100 million years. In such clusters, the combined gravity of hundreds of stars keeps them clinging to one another against the pull of the galaxy. Yet even these enduring families will, in the very long run, dissolve. Bit by bit, the Milky Way's tides and internal motions will scatter even the most tightly knit star clusters, sending their stars out on separate journeys. What began as a single star's story is in truth a communal tale. The dark cloud has given rise to dozens of stars, a whole cluster of siblings shining together. For a brief cosmic moment, they remain side by side, illuminating their birth nebula as one brilliant family. In time, they will part ways, each star travelling on its own path through the galaxy. But in these early moments, the cluster is a radiant testament to their common origin, a swarm of new suns born from the same cosmic cradle. Gradually, the nursery's veil begins to lift. The once opaque cloud that hid its stellar offspring is thinning under the assault of starlight and stellar winds. The darkness that prevailed for millennia begins to soften. Cavities open up in the nebula, and the gloom gives way to a gentle luminescence. Through the gaps, narrow beams of light start to stream out, like sunbeams piercing through morning mist. Where there were only shadows, there are now glimmers of radiance seeping through. It is a slow cosmic dawn as the newborn stars still partially shrouded, start to emerge from their cocoons. Each passing 1,000 years brings more clarity to the scene. Towering columns of dense gas, the last strongholds of the dark cloud, stand silhouetted against a growing radiance. The edges of these columns gleam, etched in light. They glow where the hidden stars' rays strike them head-on, causing the gas to fluoresce in soft reds and blues. These pillar-like remnants are the final shelters of night in a region now flooded by newborn starlight. Bit by bit, they are worn away by the very light and wind of the stars they once concealed. The pillars that once nurtured the stars are now evaporating under their glare, gently crumbling into the surrounding space. In the Eagle Nebula, home of the iconic pillars of creation, this drama is captured in breathtaking detail. Towering columns of interstellar dust and gas rise like ghostly fingers, each several light years tall and harboring nascent stars deep inside. At their tips, brilliant knots of light reveal where young suns are breaking free, their intense radiation eating away the surrounding material. Nearby, other newborn stars shine openly, illuminating the scene and casting the pillars into stark relief. The once solid spires are gradually dissolving under the glare of their progeny. Piece by piece, these cosmic crags are eroded and blown into space, destined to become nothing more than wisps. This famous vista is a snapshot of a stellar nursery in the very act of releasing its young. The Eagle Nebula's pillars of creation are just one example of nature's cosmic nurseries. Scattered throughout our Milky Way galaxy are countless similar stellar wombs. In the magnificent Orion Nebula, for instance, hundreds of young stars are condensed into a single luminous region, carving out a cavern in the gas and dust. The Carina Nebula, farther still, showcases massive newborn stars sculpting their parent cloud into fantastic shapes with intense winds and radiation. All across the spiral arms, in nebulae large and small, the story is the same. Dark molecular clouds collapse and glow, giving birth to clusters of stars. The universe is filled with these cradles of creation, each one a theatre where the drama of star birth unfolds anew. From a distance, what was once a dark, starless patch of sky begins to change. A faint glimmer appears where none was seen before. Over years and centuries, it grows steadily brighter as the dust in front of it dissipates. A once invisible star announces itself to the universe. This is the moment of revelation. A newborn star's light, having been trapped for millennia, finally breaks free of its dusty womb and shines forth. An observer far away would now see a new star where there had been only blackness. What was detectable only by its heat or gravity can at last be witnessed directly as a shining point of light in the heavens. In the end, where there was once a dense, obscure cloud, there now shines a loose cluster of young suns. The nursery's work is done. Darkness has given way to starlight. The remnants of the nebula now hang as a faint, glowing mist around the cluster, gradually fading as the years pass. The pillars and filaments of gas that dominated the scene are nearly gone, consumed or blown away by the energy of the stars. In their place is a new jewel in space, a congregation of bright stars sprinkling their light across the cosmos. The region that was once a cradle of creation has transformed into a glittering patch of sky, a new cluster adorning the galaxy with its brilliance. Interestingly, the demise of the cloud can sow seeds for new stars beyond. As the intense light and winds push against the nebula's remaining pockets, they sometimes compress more distant clumps of gas. Paradoxically, the very stars that have emerged can trigger the birth of new stars at the cloud's fringes. One by one, fresh knots may collapse, perhaps sparked by the shock waves and pressure from their older siblings' debut. In this way, star formation can propagate through a nebula, like candles lighting other candles in succession. The tips of the surviving pillars, squeezed and heated by these forces, might even give rise to another generation of protostars. Thus, the cycle of creation continues, one newborn star helping midwife the next. Every star that lights up the night sky was once a newborn in a cosmic nursery like this. Each one has its own tale of emerging from darkness, of dust coalescing to flame. By understanding the birth of this one star, we glimpse the origin story of all stars, including our own sun. There is a profound poetry in this process. Out of diffuse, lifeless gas and dust, nature kindles a shining star, a source of light and warmth that may nurture planets and life in the ages to come. It is a cycle of creation that has continued for eons and will continue for eons hence. In watching a star's birth, we witness the universe renewing itself. From simplicity emerges complexity. From darkness comes light. The pillars of creation and similar nebulae are cosmic nurseries, reminding us that even in the cold vastness of space, new beginnings are always underway. It is the end of a birth and the beginning of a new chapter. The young stars, free at last from their dusty cocoons, will now continue their journey through the cosmos. They may live for millions or billions of years, shining steadily and perhaps gathering planets around them into thriving systems. Some of those newborn worlds might one day harbour life, nurtured by the steady warmth of their sun. One day, far in the future, these stars will evolve and change, and eventually return their substance to space, sowing the seeds for yet another generation of stars. But for now, in this moment of cosmic dawn, we witness the triumphant emergence of light from darkness. The saga of these stars has only just begun. In the silent cosmic night, a newborn star emerges from its cradle of gas and dust. The faint glow of its birth gradually brightens, signaling the start of a new stellar life. Though born from similar cosmic nurseries, each star's fate is unique, determined from the very moment it blazes into existence. The key to this destiny lies in a simple but profound characteristic: the star's own mass. For a star, mass is everything. It is the master key that decides how hot the star will burn, what colour it will shine, and how long its light will endure. A small star, with only a fraction of our sun's mass, glows gently in a cooler, reddish hue. It sips on its nuclear fuel slowly, making it a model of cosmic longevity. In contrast, a giant star, many times heavier than the sun, burns with fierce intensity, a brilliant blue-white beacon flooding the darkness with energy. But this radiant blaze comes at a steep price, for such a massive star races through its life in mere millions of years, sacrificing longevity for brilliance. Under the same sky, two stars can be born in the same cosmic cloud, and yet live out radically different destinies. Imagine one star, petite and unassuming, quietly shining for eons, outliving galaxies and witnessing the cosmos evolve. Now imagine another, a titan of fire, consuming its fuel in a furious rush, destined to live fast and perish young. The contrast could not be greater. The low-mass star remains steady and enduring, while the high-mass star explodes onto the cosmic stage like a firework, dazzling but ephemeral. These divergent paths are written in their cores from the very beginning. A lighter star's core is mild and even-tempered, burning at a leisurely pace. With less gravity squeezing it, its pressures and temperatures rise only enough to sustain a gentle fusion flame. The star glows faintly, conserving its precious fuel. Across millions, then billions, and even trillions of years, it will keep shining softly. In the immense timeline of the universe, such a star may survive longer than everything we know, a quiet guardian of the night that persists when all else has changed. Meanwhile, in a heavier star, gravity's squeeze is relentless. The core of a massive star burns ferociously hot, millions of degrees, forcing atoms to fuse at a frantic rate. This star lives in a constant state of high tension, its interior roaring with energy. With so much mass bearing down, the star must produce an enormous outward pressure to hold itself up, and that pressure comes from an intense nuclear fire. The result is a luminosity that can outshine a million suns, a glorious radiance that lights up the surrounding space. Yet such a star can sustain this only for a cosmic moment. Its life, though brilliant, is tragically short, a few million, perhaps tens of millions of years, before its fuel is spent. Think of it as a cosmic trade-off. The small star is like a slow-burning candle, its flame steady and enduring through a long, cold night. The massive star is like a bonfire, fierce and hot, casting great light, but consuming itself quickly. Neither way is better or worse. They are simply different expressions of how stars live. The universe accommodates both the tortoise and the hare of the stellar world, the patient dwarf and the racing giant, each contributing to the grand story of the cosmos in its own time. Most stars in the universe take the quieter road. The vast majority are those small, faint stars, often too dim to be seen without a telescope. These diminutive stars, known as red dwarfs, account for the lion's share of stars by number. They shine with a subdued glow, sometimes only a whisper of light compared to our sun. Yet their patience is unrivaled. Even after billions of years, a red dwarf is just getting started. None that were born at the dawn of the universe have lived long enough to reach old age. The cosmos itself has not aged enough for them to exhaust their fuel. On the other hand, the rare stellar giants capture our imagination with their dramatic existence. They are born in dense clusters, often alongside dozens or hundreds of siblings. But while their smaller companions settle into long, steady lives, these giants blaze away in youthful exuberance. They dominate their surroundings, their intense radiation carving bubbles and cavities in the gas clouds around them. For a brief time, they are kings and queens of their cosmic nurseries, casting a brilliant light across the void. Our own sun sits comfortably in between these extremes, with a mass and temperament that are moderate by cosmic standards. It enjoys a lifespan of around 10 billion years. It burns neither too fast nor too slow, radiating a warm, steady glow that has nurtured life on Earth for eons. The sun is a reminder that in the middle of this wide spectrum of stellar life, there are stars that balance longevity and luminosity. Yet even the sun's eventual fate was decided at birth by its mass, just as with any other star. Through this simple difference in mass, the universe paints a variety of star lives. Each newborn star, whether a meager tenth of the sun's mass or 100 times larger, embarks on a path uniquely its own. Some will end in quiet obscurity, fading gently into the dark. Others will go out in a blaze of glory, leaving an indelible mark on their cosmic neighborhood. Every star is a story unfolding over time, from the first light of its birth to the final glow of its demise, all guided by the weight it carries in its core. As we drift among these stellar beings, we begin to sense the grand design that links a star's beginning to its end. The very gravity that pulls a star together also governs how fiercely it will burn and for how long. It is a cosmic melody playing out in variations, slow, deep notes from the long-lived stars and swift, high notes from the massive ones. In this way, mass conducts the symphony of stellar lives, ensuring each star's tune is distinct. Gently, our attention turns toward the most spectacular of these cosmic lives, the giants of fire that burn with astounding brilliance. In understanding the quiet endurance of the small stars, we can better appreciate the opposite extreme. Now, we follow our curiosity towards those massive, short-lived stars, the ones who live as giants and illuminate the cosmos with their intense, fleeting light. Their story is one of brilliance and brevity. A single massive star can be a magnificent sight, a beacon visible across thousands of light years. In the rich heart of a stellar nursery, a giant of fire takes shape alongside smaller siblings. Almost immediately, it stands apart, hotter, brighter, and larger than the rest. Its surface seethes at tens of thousands of degrees, shining blue-white, and its luminosity dwarfs that of ordinary stars. Even from afar, such a star announces itself with an intense brilliance, a lighthouse in the cosmic ocean that outshines its companions. In places like the Orion Nebula, young giant stars flood their surroundings with fierce radiation. The cluster of newborn stars at Orion's heart includes some true behemoths, each pouring out ultraviolet light that makes the surrounding gas clouds glow. These massive stars effectively light up the nebula, transforming dark cosmic dust into a colourful, luminous spectacle. Their energy sculpts and disperses the very cloud that nurtured them, clearing away the remnants of their birth cocoon. In a few million years, that nebula will dissipate, unveiled by the very stars it helped create. Life for a massive star is an exuberant blaze from the start. With so much mass, gravity crushes its core violently, igniting furious fusion even in its earliest youth. The star radiates prodigious energy, and a stellar wind of charged particles streams from its surface at millions of kilometers per hour. This wind can sweep aside nearby material, creating bubbles in the interstellar medium. If we could watch in accelerated time, we would see the giant star shedding part of itself over its brief life, forming glowing shells and nebular halos around it. As the giant star exhausts the hydrogen at its core, a process that might take only a few million years, its life enters a new stage. No longer able to sustain the same core pressure with hydrogen fusion, the core contracts and heats up even more. Helium, the ash of the star's early life, now becomes its new fuel. The star responds dramatically. Its outer layers swell and cool even as its core grows hotter. A once blue-white star can transform into a red supergiant, a bloated and cooler but still immensely luminous phase of life. The star's colour shifts toward orange and red, its outer atmosphere expanding outward many times the sun's radius. In this swollen state, the giant might engulf any nearby planets or companion stars, its girth growing vast and diffuse. High above us in the night sky, the star Betelgeuse in the constellation. Orion is a famous example of such a red supergiant. Once, Betelgeuse was likely a hot, massive star, not unlike its stellar kin. Over a mere 10 million years or so, the blink of an eye in cosmic terms, it burned through its central fuel. Now it has expanded and cooled, glowing with a somber red-orange hue. Betelgeuse is so large that if it were placed where our Sun is, it would extend past the orbit of Mars, perhaps even Jupiter. It's a giant nearing the end of its fiery life, living on borrowed time. Another luminous giant in Orion, the star Rigel, offers a contrast. Rigel shines a brilliant blue-white, a sign that it's still in a youthful, high-energy phase. It is dozens of times more massive than the Sun, and tens of thousands of times more luminous. Rigel's intense light and heat signal that it is burning its fuel ferociously. Though Rigel appears as one of the brightest stars in our sky, that brightness is a promise of its impermanence. In only a few million years from its birth, Rigel will likely exhaust its core and swell into a supergiant, just as Betelgeuse did, or end its life in a more sudden cataclysm. Indeed, the final acts of these massive stars are the most dramatic events in a star's life cycle. When a giant star can no longer sustain the fusion that supports it, the delicate balance keeping it stable crumbles. In an instant, a fraction of a second, the core of the star may collapse under its own tremendous gravity. What follows is a colossal explosion, a supernova, that rips the star apart from within. For a brief moment, the dying star can outshine an entire galaxy, unleashing more light than billions of suns combined. This is the blazing farewell of a giant, brilliant, violent, and transformative. The supernova is not an end so much as a transformation. In that explosive death, the massive star scatters the heavy elements it forged throughout its lifetime into space. All the carbon, oxygen, silicon, and iron created in its core are hurled outward, mixing with the interstellar gas. In those moments, even heavier elements are fashioned in the crucible of the explosion. Gold, silver, uranium, and more, synthesized in the fury of the blast. The stellar giant, in dying, seeds the cosmos with the ingredients for new stars, new planets, and perhaps new life. The ashes of the giant star become the fertile dust from which the next generation of stars will spring. For the giant star's core, however, a strange fate remains. Depending on its mass, the collapsed heart of the star can survive the blast as an exotic remnant. A star 10 or 20 times the Sun's mass might leave behind a neutron star, a city-sized sphere of ultra-dense matter, astonishingly heavy and fast-spinning. An even more massive progenitor could collapse further into a black hole, an object so dense that not even light can escape its grasp. These remnants are the silent epitaphs of the giant's brief life, hidden in the wreckage of the supernova, invisible reminders of the star that once shone. Massive stars are relatively few, but their influence on the cosmos is immense. They live and die on grand scales, acting as cosmic engines of change. In their short lives, they regulate the environments of galaxies. Their radiation can trigger new star formation in some places and halt it in others. Their violent deaths send shockwaves through space, compressing distant clouds and perhaps giving birth to new stars in a cosmic cycle. Without these giants of fire blazing and exploding in each generation, the universe would lack many of the elements needed for rocky worlds and living beings. And so, the giants live out their lives flamboyantly, every moment a display of extreme cosmic physics. From their turbulent birth in crowded stellar nurseries to their final spectacular demise, they encapsulate drama on a scale difficult to fathom. Yet, for all their ferocity, there is an exquisite order governing their lives. The same nuclear processes that make them shine will eventually doom them, and the very mass that gives them power also prescribes their quick decay. Their story, intense and brief, stands in contrast to the quieter stars that persist for billions of years. To truly understand what fuels these giants and indeed all stars from within, we must peer deeper, past the dazzling surface and into the core itself. There we find the secret engine driving every star's radiance. In that searing heart lies the fusion forge, where simple elements fuse into heavier ones, and light itself is born. Our journey now carries us into that hidden furnace, to witness how stars transmute matter and power their shining lives. Deep within a star's core, a transformation of matter unfolds continuously. The star's heart is a cosmic furnace, a place of crushing pressure and mind-bending heat where atoms are fused together. In young stars and in the long, stable middle age of stars like our Sun, this furnace fuses hydrogen, the lightest and most abundant element, into helium. 4 hydrogen nuclei combine in a series of steps to form one helium nucleus. And in that process, a tiny fraction of their mass is released as pure energy. Though the mass lost is small, the energy freed is enormous. Every single second, our Sun converts some 4 million tons of its own matter into light and heat. That brilliant sunshine we feel on our face is the gentle glow of mass turned into energy deep inside the Sun's core long ago, now radiating across space. This nuclear alchemy is what makes the stars shine. Hydrogen fusion is the primary source of a star's power during the longest phase of its life. In the core, temperatures of millions of degrees enable atomic nuclei to overcome their natural repulsion and merge. The star becomes a factory churning out helium ash from its hydrogen fuel. For a star like the Sun, this phase will last for billions of years. The enormous output of energy escapes the core, working its way outward through the star's layers and finally into space, providing a steady luminosity. It is a remarkably efficient and self-regulating process, as the rate of fusion adjusts naturally to maintain a balance. Enough energy to keep the star from collapsing, but not so much as to blow it apart. Over time, even the most abundant fuel runs low. When a star depletes the hydrogen in its core, a turning point is reached. In a smaller star, this might mean the end of its fusion journey. But in larger stars, and eventually in our Sun as well, the story continues with new chapters of fusion. As the core's hydrogen dwindles, the balance that held the star steady begins to waver. Gravity starts to gain the upper hand, compressing the core once more. The core's temperature climbs under this renewed squeeze until a new reaction ignites. Helium fusion. Helium fusion, often called the triple alpha process, fuses 3 helium nuclei into one carbon atom. This marks a second act in the star's life. When helium ignites, it does so explosively in the case of medium-mass stars like the Sun, a brief burst called the helium flash, after which the star settles into a new equilibrium. In more massive stars, helium begins fusing more gradually, but in all cases, the result is the creation of carbon, and often oxygen as well, in the core. The star has now forged elements that did not exist in its core before, elements that will be crucial building blocks for planets and life outside the star. If the star is massive enough, the fusion saga continues. Once helium is exhausted in the core, carbon can take its turn as fuel. Carbon atoms fuse into heavier elements such as neon, sodium, and magnesium. Each new fuel requires more extreme conditions to ignite, higher temperatures, greater pressures, conditions only found in the cores of very massive stars. The sequence continues. After carbon, neon may fuse into oxygen and magnesium. Oxygen can fuse into silicon and sulfur, and then silicon eventually fuses into iron. With each step, the star builds up layers in its interior, an inner core of the new heavy element, surrounded by shells where earlier, lighter elements are still fusing. A truly massive star in its old age resembles a cosmic onion, with concentric layers of burning shells, hydrogen around helium, around carbon, around oxygen, and so on, all glowing at once in a complex nested inferno. At this advanced stage, the pace of life accelerates drastically for a massive star. The early chapters, hydrogen and helium fusion, span millions of years, but the later chapters rush by. A massive star might spend mere thousands of years fusing carbon, only a handful of years burning neon, and perhaps months consuming oxygen. In its final throes, it burns silicon into iron for only days or weeks. The core, by then composed of iron and nickel, grows like a hot, dense ember at the center, inert and unburnable. Iron is nature's fusion ash. When lighter elements fuse into iron, they reach the end of the road in terms of energy gain. Fusing iron does not release energy. Instead, it consumes energy. So as iron accumulates in the core, the star's furnace is inexorably dimming, preparing for a dramatic finale. Smaller stars never tread this path of forging heavy elements. A star like our Sun will stop after creating carbon and oxygen. It simply cannot squeeze and heat its core enough to ignite further fusion of those elements. Instead, once the Sun's helium fuel is spent in the distant future, its core will be left as a cooling ball of carbon and oxygen, the ember of a star that was, destined to become a white dwarf. The great gift of massive stars is that they carry the fusion process to its limits, crafting the heavy elements that fill the periodic table. Without massive stars, forging elements like silicon, iron, and beyond, in their explosive ends, the universe would be a poorer place in chemistry and color. Every atom of carbon within us, every oxygen molecule we breathe, was once cooked in the heart of a star. Long before our Sun existed, earlier generations of stars lived and died, bequeathing their enriched guts to the galaxy, the calcium in our bones, the iron in our blood, the gold in our jewelry. These owe their existence to stars that burned billions of years ago. In life, those stars quietly transmuted light elements into heavier ones. In death, they scattered them across space. Our world, and indeed we ourselves, are made of stardust, star-forged matter flung from ancient supernovae, now gathered into new forms. Thus, the cores of stars are the universe's crucibles, and fusion is the alchemy that drives the cosmos onward. Through fusion, the darkness is lit with starlight, and simple atoms become the seeds of complex worlds. This tremendous energy release is what holds stars up against gravity's pull. As long as a star has fuel to burn, the outpouring of energy from its core creates an outward pressure. That pressure balances the inward force of gravity, and the star remains stable, neither collapsing nor bursting apart. Herein lies a beautiful secret of the star's longevity, a harmony of energy, a balance between opposing forces. To understand how stars can maintain this balance for such astonishing lengths of time, we now explore that delicate equilibrium, the graceful dance that keeps a star shining steadily for eons. Stars appear to shine with an unchanging light, tranquil and eternal to our eyes. Yet behind that calm facade is a continuous balancing act of colossal forces. Gravity, the force that brought the star into being, is always pulling inward, striving to shrink the star and crush it further. Opposing this is the pressure generated by the star's own heat and light. the outward push of all the energy streaming from nuclear fusion at the core. A star lives its life in a state of hydrostatic equilibrium, a graceful balance where gravity's inward pull is exactly matched by the outward push of pressure. In this equilibrium, the star finds stability, maintaining its size and shine for millions or billions of years. This balance is delicate, yet remarkably self-sustaining. If, for any reason, the core of a star produces slightly less energy, gravity will gain a momentary advantage and pull the star's core inward more strongly. But this contraction heats the core up, and the increased temperature causes fusion to speed up once again, releasing more energy. The extra energy pushes back, and the star expands slightly, restoring the balance. Conversely, if the fusion reactions begin to overshoot and produce too much energy, the star's outer layers will be pushed outward. The star swells a little, which cools the core and slows the fusion reactions, easing the pressure. In this way, the star regulates itself like a cosmic thermostat. Small oscillations occur, but they are gently damped out as the star returns to its poised state. For long stretches of a star's life, this tug-of-war remains in near-perfect harmony. Our Sun, for instance, has been in such a steady state for around 4.5 billion years, and it will remain so for several billion more. During this time, its radius and energy output change only gradually. The sunlight bathing Earth today is nearly the same as it was for the dinosaurs long ago, a testament to the Sun's stable equilibrium. The star's heartbeat is slow and constant, a comforting steadiness in the otherwise tumultuous cosmos. Different stars conduct this balance in different ways. A small red dwarf, cool and dim, holds its equilibrium with a relatively gentle internal pressure, pushing against a modest gravitational tug. It can maintain this quiet stasis for an extraordinarily long time, sipping fuel so slowly that its balance might hardly waver over trillions of years. A massive star, by contrast, achieves a more precarious balance. With gravity's pull so intense, its core must generate an immense pressure to hold the star up. The equilibrium is maintained, but at the cost of a furious rate of fusion. The massive star's life is like a high-wire act. The stakes are higher, and the balance, while real, will be shorter-lived. The star will only manage to sustain equilibrium for a few million years before the scales tip and evolution to the next stage begins. Yet, for each star, high mass or low, there is a serenity in this balance. It's as if the star is in a meditative state, inwardly burning and outwardly shining, but outwardly calm and composed. Within, the forces of nature are engaged in an endless dance, gravity pressing in, energy radiating out, neither ever fully defeating the other until the fuel begins to wane. This is the secret to a star's longevity and consistency. It spends the majority of its life not in chaotic change, but in this peaceful stalemate, steadily glowing. The harmony can last only as long as there is sufficient fuel in the core. When eventually the core's fuel is nearly gone, the balance falters. Gravity starts to tighten its grip unchecked, and the star responds dramatically, swelling or shedding its outer layers to find a new balance at a larger size or different structure. In such moments, the star's outward tranquility is broken, and it enters a new phase of life or death. But until that point, hydrostatic equilibrium is the star's guiding principle, its silent promise of constancy. In truth, stars are not utterly static, even in their equilibrium. They are dynamic, living spheres of plasma. Often they carry subtle pulses and vibrations within their vast bodies, tiny rhythmic tremors that ripple through their hot gas. The star's equilibrium acts like the tension on a drum or violin string, setting the stage for vibrations to occur. These are usually imperceptible to the naked eye, and yet they form a kind of music, a silent chorus ringing through the stellar interior. Every star, in maintaining its balance, may also be quietly singing. To delve into this hidden music, we must listen to the stars themselves and learn to detect the gentle songs that reveal their inner nature. In the vacuum of space, true sound cannot travel, yet stars still manage to fill the cosmos with a silent music. When we observe a star closely over time, we find that its light sometimes rises and falls ever so slightly in regular patterns. These gentle flickers are the signatures of waves pulsing through the star's interior, the star's subtle song made visible. As the star's hot gases swell and contract, pressure waves bounce within, much like sound waves in a musical instrument. Though no air carries the sound to our ears, the star's surface responds, and its brightness oscillates in sympathy with these internal vibrations. Through careful measurement, astronomers have learned to hear these stellar vibrations, translating the faint cycles of light into cosmic music. Every star's song is unique. Larger stars might boom with slower, deeper throbs, while smaller stars tremble with quicker, higher-toned oscillations. Some stars vibrate in many modes at once, creating a complex chorus of frequencies. It's as if each star is an instrument playing a tune that reflects its own composition and structure. From these stellar songs, we can decipher the hidden layout of a star's interior. The way the waves travel and interfere tells us about the density and temperature deep inside, much like the tone of a bell reveals its shape. In this way, without ever touching a star, we come to know its inner heart, reading the vibrations as a code that unlocks secrets of the star's mass, age, and even the size of its core. Our own sun was the first star whose music we detected. The sun's surface ripples ever so slightly, rising and falling with a myriad of tones excited by its turbulent convection. By studying these solar oscillations, a field known as helioseismology, scientists mapped the sun's interior with astonishing precision. They discovered that our star rings like a bell, with millions of individual sound waves trapped inside, overlapping to produce complex patterns. Building on this knowledge, we realized that other stars too experience such quivers. In recent times, space telescopes have stared at distant stars, recording their brightness with enough accuracy to catch these minute fluctuations. The data revealed an orchestra of stars, each humming its own tune across the galaxy. Some stars carry their rhythm on a grander scale, their music audible in the form of changing brightness, even to early astronomers. Cepheid variables, for example, are giant stars that pulsate in size and luminosity in a steady beat. These stars brighten and dim as they expand and contract, their periods ranging from days to weeks. A Cepheid's pulse is so regular that it has been likened to a stellar heartbeat, one you can set your clock by. Early in the 20th century, Henrietta Leavitt discovered that the length of this pulse was related to the star's intrinsic brightness, making Cepheids invaluable beacons for measuring cosmic distances. Thus, the loud beats of Cepheid stars have guided us in mapping the universe, each throbbing star a lighthouse in the void. Yet for most stars, the music is quiet and requires patient listening. This stellar music carries profound information. The slight change in tone can reveal if a star's core is mostly hydrogen or if it has built up a cache of helium ash. It can tell how old a star is by showing how much it has evolved internally. In red giant stars, oscillations reveal the presence of a compact core and an expansive envelope, distinguishing them from younger stars. In young blue stars, certain patterns of vibration can even hint at how fast their cores are spinning. These discoveries are possible because the star's vibrations depend intimately on its internal characteristics, and by decoding the patterns, we infer what must be within. There is poetry in realizing that the stars not only shine, but sing in their own way. The universe, often perceived as silent, is in fact filled with this perpetual chorus. We cannot hear it with our ears, but the music of the stars is all around us, written in their flickering light. Each twinkle we see in the night sky may be more than a random shimmer. It can be a star's subtle symphony playing out over eons. By attuning our instruments to these delicate variations, we have joined the cosmic audience, listening to stars as they tell their stories through song. As we lift our gaze from individual stars and their intimate music, we step back to behold the entire stellar tapestry. The night sky above is a grand stage where countless stars perform together. Each dot of light, each star with its own hue and character, contributes to the silent symphony of the cosmos. United, they paint the darkness with a radiant spray of color and melody, inviting us to contemplate a sky full of suns, each one a world unto itself. On a clear, moonless night, far from city lights, the sky becomes a dark canvas, spattered with starlight. Thousands of pinpoints gleam against the black, each one a distant sun. To the unaided eye, they mostly appear silver or white, but look more closely or through a telescope, and a rainbow of star colors emerges. There is the cool red glow of stars, like Betelgeuse, an amber hue that signals a giant's old age and cooler surface. Not far away in the sky, the star Rigel shines with an icy blue-white light, its color betraying intense heat and youthful energy. Golden Arcturus, brilliant Sirius, delicate Vega. Each star adds its own shade to the night. Together, these diverse lights paint the heavens with subtle color and tell of a rich variety in stellar life. These colors are not just for show. They are clues to the nature of each star. A star's hue is like its personal signature. Blue and white stars are extremely hot, often massive, and burning their fuel at a prodigious rate. Red stars are cooler. Some are small, dim dwarfs glowing softly for eons, while others are bloated supergiants nearing the end of their life. Between are stars like our sun, shining in gentle yellow-white, moderate in both temperature and lifespan. The night sky's palette is the result of these differences. Each point of light is a story at a different chapter. Some are just beginning to blaze, others are in their tranquil midlife, and a few are fading elders. It's humbling to remember that the stars we see with our eyes are only a tiny fraction of those that exist. Out of the 100 billion or more stars in our galaxy, only a few thousand are visible without aid, and those tend to be the most luminous or nearest to us. The Milky Way itself arches overhead as a pale milky band, because it is the combined glow of countless stars, too distant and faint to pick out individually. We gaze at that gauzy band and realize it is the soft light of billions of suns, overlapping like countless candle flames seen from afar. In every patch of dark sky where the eye sees nothing, a telescope reveals yet more stars scattered like fine dust. The universe is vast and filled with stars beyond numbering, each one a beacon in the dark. Amid this immense gathering of suns, our own sun is just one modest star. If you were on a planet circling another star, our sun might be just another inconspicuous point of light in that alien sky. Nothing about its appearance would hint at the life it nurtures here, or the significance it holds for us. And just as our sun is an ordinary star in the grand scheme, Many of those stars we admire from Earth might have their own families of planets, and perhaps life of their own. When we contemplate a sky full of suns, we are really contemplating the potential for endless worlds and stories scattered across the cosmos. Each star could be the center of its own system, a sun giving warmth and light to orbiting planets, some barren, others may be lush with life, gazing back at the stars in their sky. The night vista we behold is a snapshot in an ever-changing theatre. Stars are not eternal. The constellation patterns we know are fleeting on cosmic timescales. Over millions of years, stars move, new stars emerge, and old ones expire. If we could watch the sky over eons, we'd see stars appear where none were before, and familiar stars vanish as they exhaust their fuel. The Orion we recognize today would gradually morph as its bright stars age and fade away. Even the gentle band of the Milky Way will alter as generations of stars are born and die within it. The sky is alive, though its changes are too slow for a human lifetime to notice. It reminds us that creation is ongoing, and we are witnessing just one moment in a grand cosmic evolution. There is a profound connection between the stars that shine now and those that will shine in the future. Massive stars will end their lives in cataclysms, spreading their enriched guts into space as glowing nebulae. In those scattered ashes, new stars will spark to life, inheriting the elements of their predecessors. The cycle ensures that the death of stars leads to the birth of new ones, each generation seeding the next. When we admire the glistening night sky, we are also seeing this cycle in various stages. Some stars in their youth amid nebulae, others approaching their final twilight, and the remnants of long-gone stars faintly visible as misty clouds. The cosmos recycles its brilliance. As our journey through the lives of stars comes full circle, we recognize that every star in the sky, no matter how different, shares a common destiny: to be born, to shine, and eventually to pass on its light to the next era of stars. The pillars of creation stand as silent witnesses to this ongoing saga. Clouds of gas and dust lit by newborn stars, containing the remnants of older ones. A sky full of suns is a sky full of stories, of fiery births and quiet middles, of explosive ends and new beginnings. Though we have traced the arcs of stellar lives, the cosmic story is far from over. In the silent awe of the night, under a canopy of ageless starlight, we sense that there are more chapters yet to unfold in the epic tale of the stars. We stand witness to the final, violent act of a stellar life, as a massive star collapses under its own weight. In the dimming light of its final days, the star's core, once a furnace powering nuclear fusion, can no longer hold back gravity. The immense pressure forces iron nuclei to disintegrate, unleashing a flood of neutrinos as an unstoppable implosion begins. For a heartbeat, the star's center is gone, and yet within that collapse lies the spark of new creation. Suddenly, the imploding core rebounds. A shockwave races outward through the star's layers, carrying unimaginable energy. In an instant, the star's outer shell explodes in a supernova, a brilliant flash that can outshine entire galaxies. The once proud giant is no more, its final light fading into the cosmic darkness, leaving behind only echoes of its powerful demise. The sky trembles with the power of this collapse. Even as the star vanishes in a flash, its explosive death seeds great swathes of the cosmos with its innermost elements. Enormous stellar furnaces have been broken apart, scattering iron, oxygen, carbon, and heavier elements into the void. In this explosive moment of death, there is both destruction and creation entwined. As the star's death throes sow the seeds for future celestial life. The light from a supernova travels across the universe, a beacon announcing the death of a star. We might witness such an explosion through a powerful telescope, seeing it as a temporary new point of light in the sky. This flash is the culmination of processes hidden deep inside the star for millions of years. It reminds us that the cosmos is alive with dramatic events, even in the vast quiet of space. Scientists believe that for a brief moment, a single collapsing star emits more energy than the entire galaxy that hosts it. The explosion's fury originates in those final seconds, as the core buckles and neutrons pack together. Vast quantities of neutrinos burst outward, almost unseen, but carrying away energy that helps power the explosion. Then, as quickly as a candle's flame in the wind, the fire of the star is gone, and all that remains is a swiftly expanding shell of gas and dust. In the aftermath, the star's death is far from quiet. The expanding shockwave plows through space, driving a cosmic wind that sweeps up interstellar material. It carves a cavity in the surrounding gas, almost like a footprint left by a cosmic giant's final step. This turbulence ripples outward, a reminder that the death of a star is not silent, but a dramatic event that echoes across light years. Deep within the imploding core, the laws of physics are stretched to the extreme. Atoms are crushed into their components, and protons and electrons fuse into neutrons in a heartbeat. A teaspoonful of that collapsed core would outweigh a mountain. From this furious collapse, an enormous wave of neutrinos surges outward. Though we cannot see them, these ghostly particles carry away unfathomable energy, fueling the shockwave that ruptures the star's outer shell. This cataclysmic death has subtle preambles and echoes that only science can catch. In 1987, telescopes watched a star explode in the nearby Large Magellanic Cloud. Before its light reached us, particle detectors here on Earth picked up a quiet burst of neutrinos, the invisible messengers of the collapse. It was as if the universe whispered first in secret before lighting the sky. Such events remind us that even in violent death, there is information hidden, like a message in the cosmos. Not every giant's death is visible to us. The most massive stars might collapse so completely that light itself cannot escape. In these cases, the star seems to vanish into the night, leaving no brilliant fireworks behind. Such a disappearance hints at a black hole quietly forming at the center. But even then, the star's death still plays out in powerful ways. Regardless of the final fireball we glimpse, the star's essence must go somewhere. Its outer layers are flung outward or quietly shed, and its core becomes an object of staggering power. Either the core compacts into a tiny star made mostly of neutrons, or it collapses so fully that not even light escapes. In either case, the once mighty star lives on in a new form. Its death has transformed it into one of the universe's strangest survivors. From the ashes emerges something almost unimaginable. Crushed by the supernova's force, the star's core can condense into a neutron star. In a small sphere, only a few tens of kilometers across, a mass greater than our sun is compacted. This is no ordinary object. Its gravity is crushing, its density such that a teaspoon of its material would weigh as much as a mountain. Neutron stars are survivors turned exotic. They can spin at dizzying speeds, some rotating dozens of times each second. Magnetic fields, trillions of times stronger than Earth's, surround them, flinging particles into space with ferocious energy. For a while, The dead star burns not with nuclear fire, but with magnetic power. These stellar remnants shine in X-rays or radio waves, invisible to our eyes, but real and potent in the cosmic night. Many neutron stars become pulsars, cosmic lighthouses in the dark. From our perspective, they appear as regular pulses of light or radio signals, each flash as precise as the ticking of a clock. Imagine the inner core of a star hurtling through space, its beams sweeping across the universe like the sweep of a beacon across the ocean on a foggy night. The Crab pulsar in the famous Crab Nebula pulses 30 times a second, a heartbeat left by a star that exploded long ago. Some neutron stars grow ever stranger. Magnetars are cousins with even more intense magnetism. Their fields twist space and time, occasionally snapping and unleashing bursts of X-rays and gamma rays. In that sudden flare, they can briefly outshine even supernovae. These objects reveal that the death of a star can yield the most magnetic and mysterious bodies in the sky. Even stranger fates await the most massive cores. If the remnant's mass is too great, not even neutron degeneracy pressure can hold it up. The core collapses further into a black hole. This object is a vacuum in space, an abyss of gravity from which nothing, not even light, can escape once it crosses the event horizon. The newly formed black hole silently consumes any matter and radiation that venture too close. A black hole is the ultimate secret of stellar death. Imagine space itself, bent inward, like a well with no bottom. Cross the threshold, known as the event horizon, and you are gone forever. We can never directly watch what falls past that boundary. Yet even from a distance, black holes announce themselves. Gas swirling into the abyss heats up and glows in X-rays. Stars orbit around an empty point in space, revealing the ghostly presence of these objects by the gravitational tug. In this way, even the darkest objects leave a trace. These strange remnants wield immense power in their own right. A swiftly spinning neutron star drives a wind of particles that can blow a glowing bubble in the leftover gas. It effectively lights up the darkness around it, a cosmic lantern powered by magnetism. Meanwhile, a black hole may silently draw in gas or even a companion star, heating the infalling material into brilliant X-rays before swallowing it. Each remnant continues to shape the universe, teaching us about physics in extreme conditions that we cannot reproduce on Earth. As the supernova fades, it leaves behind more than just a remnant. It leaves a legacy. Every atom of oxygen in our air, every speck of iron in our blood, was once forged inside a massive star. When that star exploded, it spewed these heavy elements into space. The death of stars is therefore a cosmic recycling program. It transforms the basic hydrogen and helium that suffused the universe after the Big Bang into the diverse array of elements that make up planets, life, and even future stars. Inside a star's life, lighter elements fuse to form heavier ones. Hydrogen into helium, helium into carbon and oxygen, and onward to silicon and iron. But iron is the limit of the peaceful fusion fires. To go beyond iron, nature requires an even more violent catalyst, the supernova explosion itself. The explosion's neutron-rich fury forges the very heaviest of all. In its split-second blast, gold and silver, the rarest metals on Earth, are synthesized among a flood of neutrons. When a star dies, it gifts the cosmos with the raw materials that shape our world. We can picture the galaxy as a grand recycling facility. Clouds of gas, once pure hydrogen, become seeded with star stuff after each death. With each generation, the material becomes richer in heavy elements. By the time our own sun formed, the gas was already enriched. Planets could form and life could evolve. Every time a massive star lives and dies, it imprints the universe with a new cache of materials. The ashes of stellar death become the building blocks of new worlds. In time, the chaos of the explosion settles into a quiet spectacle. The ejected gas and dust become a supernova remnant, a nebula bathed in ghostly light. These vast structures can span light years across, glowing with the elements that were once the star's innermost layers. Viewed through telescopes, they appear as a tapestry of filaments and bubbles, softly illuminated by the energy left behind. It is as if the star's death has painted the heavens with a haunting, otherworldly beauty. The colours of these nebulae are coded by chemistry. Hydrogen, in the expanding shell, often glows with a red tint, while oxygen can shine in a pale green. Though invisible to us unaided, the remnant's radiation warms up atoms that then release light in these hues. The twisting, filamentary shapes are sculpted by shock waves and magnetic fields, like wisps of luminous smoke frozen in time. Observatories that detect X-rays or radio waves reveal these ghostly clouds as zones alive with particles traveling near light speed. Consider the famous Crab Nebula in the constellation Taurus, the lingering remains of a supernova recorded by sky watchers in 1054 AD. It is one of the brightest and most studied remnants, an irregular web of glowing threads that still pulses with energy. At its heart spins the Crab pulsar, the fast-rotating neutron star sending ripples through the gas. This example shows how a star's death can linger as an object of enduring fascination across centuries. There are many other such remnants scattered across the sky, each with its own story of life and death. These nebulae of ghost light change slowly over time. Over years or centuries, they expand and fade, but the outline of their structure remains visible. They remind us that space is not static, but in motion, its vast currents shaped by ancient events. To observe a supernova remnant is to peer deep into history, for the light we see may have begun its journey long before the dawn of human memory. In this way, they connect us to the cosmic past, preserving moments of time in spectral form. The beauty of these cosmic clouds lies in their stillness and their quiet vitality. Though they expand into emptiness, the energy within them keeps glowing. Shock waves and magnetic forces mold their shapes, giving them an almost living aspect. We call them nebulae of ghost light because they are the shining ghosts of stars, silently haunting the dark. Even in death, a star plants the seeds of new life. The shockwave from the explosion spreads outward and encounters other clouds of gas and dust. Where the wave crashes into a dense region, it compresses the gas, sometimes triggering the cloud to collapse under its own gravity. From this collapse, new stars begin to form. In this way, the death throes of one generation can spark the birth of the next. We see this process in many corners of the sky. Giant molecular clouds, already on the brink of collapse, can be pushed over the edge by a passing shock. Observatories have caught glimpses of star nurseries just as they ignite, often at the edges of cavities carved by ancient supernova. In a sense, each sunset of a star becomes a sunrise for another. The ruins of the old become the womb for the new. Our own solar system may carry the signature of such an event. Clues in meteorites and in the elemental makeup of Earth hint that a nearby supernova enriched the cloud that formed the sun and planets. If true, the atoms of our bodies and our world were once part of that exploded star. We are, quite literally, children of cosmic fire. Each human heartbeat is nourished by elements forged in the hearts of stars. When we look at the night sky, we may think of stars as fixed and eternal, yet on cosmic timescales, they are in constant flux. Galaxies pulse with cycles of star birth and death, as if breathing. The life and death of stars weaves the universe into a living tapestry. Each explosion is like an exhalation, releasing enriched material into space. Each new star-forming cloud is like an inhalation, drawing in that material to create something new. In this grand rhythm, even our own sun is part of the inhale-exhale of the cosmos. Time in this perspective becomes vast and continuous. A star's millions of years lifespan is but a single heartbeat. Generation after generation of stars come and go, each building upon the ashes of those that came before. The galaxy itself grows more intricate with every stellar cycle. There is no definitive end or beginning, only an endless flow. The cosmos renews itself forever, epoch after epoch, without ever drawing a final breath. Our very existence is woven into this cosmic rhythm. The Earth, our Sun, and all life on our planet are products of this cycle of death and renewal. The iron in our blood and the calcium in our bones were forged inside stars, long gone. When we gaze up, we see light from distant suns that may have died long ago. Knowing that connects us to the universe on a profound level. We are literally made of star stuff, living actors in a drama of creation that spans the cosmos. There is a quiet comfort in understanding this cycle. It is neither abrupt nor tragic, but a gentle song played out over eons. Each star's end is also a beginning for something else. Even after billions of years, the pattern remains. Stars are born, they shine, they die, and from their remnants, new stars emerge. This reveals a simple truth. Change is the only constant, and creation and destruction are forever intertwined. So we move forward on our journey, filled with wonder and humility. Each discovery about the universe's cycles awakens new questions. There will always be more to learn in this cosmic story. The adventures that await are beyond what we can imagine. The universe continues to breathe, its story carrying onward from one generation of stars to the next. Like a delicate spider's web stretching across the cosmos, the universe is woven from filaments of gas and galaxies. These threads extend for hundreds of millions of light years, drawing galaxies together in a vast cosmic web. Within this network, clouds of hydrogen and helium slowly flow along invisible lines, feeding the formation of new stars. This tapestry of space and time reminds us that every star's birth is connected to a larger story. As gravity pulls the gas along these filaments, galaxies gather at the intersections, creating nurseries of light among the darkness. Over billions of years, these cosmic highways have guided matter through the dark void. Ancient clouds of gas and dust flowed along them, carrying the seeds of future stars from one galaxy to another. As the universe expanded and aged, these threads acted like lanes in time, connecting past and present. The light we see from those distant galaxies on the threads has often taken millions or even billions of years to reach us. Each glowing nursery we observe is a window into the past, its light echoing across the ages. Through this cosmic infrastructure, star formation links different eras, weaving the present with the distant past. Astronomers have mapped these filaments like explorers charting unknown seas, tracing the hidden structure of the cosmos. Surveys of millions of galaxies and powerful computer simulations reveal a web threaded with clusters and voids, a grand pattern writ large. It is as if the sky has an invisible scaffolding that guides the formation of stars and galaxies. Each point of brightness on these filaments is both a starry metropolis and a signpost in the cosmic chronicle. In this universal network, the births of stars are not random events, but part of an intricate design. Each new star contributes its light to the loom of the universe, reinforcing the threads that bind galaxies and time. Invisible forces shape this grand design. Dark matter underpins the cosmic web. Gravity, acting through both visible and dark matter, draws gas and galaxies into these long filaments. Computer simulations show that dark matter forms a similar web first, and then ordinary matter follows along these paths. We cannot see dark matter directly with our eyes, but its influence is clear. It acts as an unseen scaffold holding the universe together. Everywhere matter gathers, a gravitational chorus pulls in more, reinforcing the web's strands over cosmic time. Billions of years ago, as the first stars and galaxies flickered into existence, they were already gathering along these cosmic avenues. The densest intersections of the web became cradle sites where the first galaxy clusters took shape. As time marched on, the web grew more defined, and each new generation of stars added to its intricate tapestry. Our own galaxy, the Milky Way, is perched on one of these filaments and has encountered smaller galaxies on its journey along the strand. By tracing this web back through time, we see that the universe's current tapestry was woven one thread at a time, ever more elaborate with each epoch. Even as we observe it today, the web of creation continues to stretch outwards, a record of eons of cosmic evolution. Between the threads lie vast cosmic voids, regions almost empty of matter. These pockets of nothingness accentuate the web, highlighting how material has been pulled into the strands over eons. Within the filaments, gas is denser and more easily clumps into stars, whereas the voids remain still and dark. The contrast between bright bridges and dark emptiness highlights how the cosmic web concentrates the raw ingredients for creation. It is as if the universe has organized itself into a grand pattern, where the lights of stellar cities dot the darkness of an unseen countryside. Thus, the very structure of space guides where creation is most vibrant, making a patchwork where pockets of light spark out of nothing. We cannot see the cosmic web with our eyes, but imagination paints it across the sky when we contemplate the stars. If the universe were a city, these filaments would be its streets and highways, guiding the flow of traffic in the form of gas and stars. The web's beauty lies in its simultaneous simplicity and complexity. Simple threads connecting galaxies, yet spanning the entire observable universe. As telescopes and maps reveal more of these connections, we gain a sense of cosmic order, a hidden blueprint behind the grandeur of the heavens. Each galaxy's light tells a story of billions of years, hinting at the network that binds it to others. In every sense, star formation is not just a local event, but part of a majestic architecture that stretches across the cosmos. The cosmic web story begins at the dawn of time, when tiny ripples in the primordial plasma were stretched by cosmic expansion. These faint fluctuations, imprinted in the cosmic microwave background, became the seeds of everything we see. Over eons, gravity amplified these seeds into the vast filaments of gas and dark matter that now span the universe. In every direction we look, the structure of the cosmic web reflects that ancient imprint, a fossil record of the universe's beginnings. Thus, star formation today is linked to processes set in motion billions of years ago. Each new star that bursts to life emerges from a framework that was woven in the very first chapters of the cosmos. Astronomers discovered evidence of this web by analyzing distant quasars, whose light shines through the intergalactic medium. When a quasar's beam passes through a filament, it leaves faint absorption lines in the spectrum, like shadows that trace the threads of gas. These observations confirmed that the universe is threaded with matter in the places predicted by our models. Similarly, large surveys of galaxies reveal a pattern where galaxies align along filamentary structures. In effect, we have mapped the cosmic highway system in reverse, from the clues left in the light of faraway sources. This knowledge lets us appreciate that every speck of light in the night sky is part of a vast, interconnected network. Imagine drifting along one of these cosmic filaments, like a ship in space. Over vast stretches of time, you would pass nebulae birthing stars, encounter clusters of galaxies lighting up the path, and witness the silent aftermath of ancient supernova echoing in the darkness. This journey would reveal that even in the quietest regions, the history of the cosmos is written in the distribution of matter. Every point of light and every shadow we see from Earth is a part of that journey, a waypoint on the grand voyage of cosmic time. We may not actually traverse these highways, but through telescopes and thought, we travel their length and breadth. In this way, by studying the cosmic web, we come to know the universe and our place within it in a deeply intimate way. The cosmic web not only shapes where stars form, but also how galaxies move. Galaxies drift along these filaments, pulled toward the dense knots where multiple threads intersect. Collisions and mergers between galaxies often happen at these nodes, creating some of the most active star-forming regions. By observing this dance of galaxies, we learn that the filaments are like rivers, with galaxies moving along their currents. Even our own Milky Way has absorbed smaller galaxies drawn in from the web. In this way, the cosmic web is not a static pattern, but a dynamic river system of creation and movement. Thus, the cosmic web teaches us that nothing in the universe is truly isolated. A star forming in a distant galaxy is part of the same grand process that forged our own sun. Each filament and node is a chapter in a narrative that spans the cosmos. When we understand the web, we see how star formation connects galaxies and eons of time. It reminds us that our story, and every star's story, is written into the fabric of the universe. Every light we see is a message carried along these filaments, linking our fate with the stars. Each element in the periodic table tells the story of a star. The helium in neon lights, the iron in skyscrapers, the iodine in our salt, all have stellar beginnings. This grand realization extends science beyond our world and binds the entire universe into one narrative. As we continue our journey, we will see how our quest to understand this alchemy has led us to build incredible new eyes on the universe. Within the heart of each newborn star lies a secret of creation and transformation. At their cores, immense pressure and searing temperatures ignite nuclear fusion, alchemizing simple hydrogen into more complex elements. This chain reaction starts with hydrogen fusing into helium, releasing enormous energy that makes the star shine steadily for millions or even billions of years. Stars remain remarkably stable during this phase. as if burning with a controlled flame far denser than anything on Earth. In larger stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen, and in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the process continues through multiple burning stages. Helium atoms collide to form carbon and oxygen. And in even more massive stars, the stars, even heavier elements like silicon and iron, are born. Over time, a star becomes a living factory for creating elements, each nuclear reaction building layer upon layer of new material. In a sense, the star's life story is written in its core. Each chapter is a new element forged under unimaginable conditions. Each photon of starlight carries the proof of this process. The glowing remnants of fusion travel outward, bearing the story of creation across the cosmos. To astronomers, the light of a star is like a record of its heart's work. In time, massive stars exhaust their fuel and end their lives in brilliant supernovae, scattering enriched matter across the galaxy. These explosions shine with the light of 1 billion suns and can be seen from millions of light years away. Through the violence of a supernova, carbon and oxygen are fused into elements heavier than iron, including gold, platinum, and uranium in the blink of an eye. Such cataclysms mark both an end and a beginning, as death gives way to new creation among the ruins of the old. Some stars end their lives more quietly. Moderate mass stars swell into red giants and shed their outer layers slowly, releasing carbon and nitrogen into space without a dramatic explosion. These stellar winds act like cosmic gardeners, fertilizing the galaxy with the building blocks of life. Every supernova and stellar wind event is a gift to the universe, seeding future star nurseries with raw materials. This cosmic cycle means that every atom of gold, every grain of calcium on Earth, was once forged in the core of an ancient star. The planet we call home is built from the remnants of these ancient fires. Billions of years ago, clouds of gas enriched by countless stars collapsed to form our solar system. Our Sun is an example of a star in this cycle, born from material left behind by earlier supernovae. From the iron core of the Earth to the oxygen in our atmosphere, each element carries a piece of a star's life. The rocks under our feet, the mountains above, and the water that filled the oceans were all born in stellar furnaces. In this way, the dust of long-dead suns became the cradle of life. Every mountain range and every drop of water on our planet carries the fingerprint of cosmic alchemy at work. Step by step, each star builds the ingredients of the universe. Hydrogen atoms fuse into helium deep in the core, and helium can fuse into carbon, oxygen, and even heavier elements like magnesium and silicon, the very basis of planets. In massive stars, the process marches onward to create elements up through iron on the periodic table. Then comes the finale. To forge elements heavier than iron, nature requires cataclysmic events. Supernovae and neutron star collisions become the cosmic forges that create the rare materials like gold, iodine, and uranium so precious to us. Without these stellar furnaces, the universe would remain a simple place, lacking the rich complexity needed for planets, oceans, and biology. The oxygen we breathe, made by ancient stars, carries the legacy of those stellar furnaces into each new sunrise. In fact, everything around us, every element beyond hydrogen and helium, is a gift from past generations of stars. We can read this cosmic chemistry in the light of stars. Each element absorbs and emits light in characteristic wavelengths as atoms dance to the laws of quantum physics. This gives each atom a unique fingerprint that astronomers can detect with spectroscopy. By analyzing these spectral fingerprints, scientists determine which elements are present in distant nebulae and galaxies. Light becomes a messenger from faraway laboratories, carrying news of carbon-rich clouds or iron-poor stars. It tells us that silicon and oxygen float in the heart of a cloud, that iron glints in a distant young star, and that carbon is plentiful in a galaxy far away. Each photon is a courier of chemical secrets, revealing the alchemy that turned gas into planets, oceans, and life itself. We can explore these hidden realms because humanity has built ingenious eyes in the sky. From Galileo's first telescope to the Hubble Space Telescope and beyond, our tools have grown ever more capable. Powerful observatories now scan the cosmos in every direction and wavelength, from radio waves to X-rays. They allow us to peer beyond the veil of dust and gas that would otherwise obscure star formation. Every generation of instruments reveals new depths of the universe. Each wavelength tells a different part of the story. Infrared reveals warm dust cocoons where stars form. Ultraviolet highlights young hot stars, and X-rays show the chaotic afterlife of dead stars. By combining these perspectives, we begin to see the full picture of cosmic alchemy unfolding. In doing so, we learn not to be limited by the senses nature gave us, but to reach ever farther with our instruments. Thus, human curiosity, paired with technology, extends the cosmic web of knowledge, connecting us directly to the very processes that shaped our existence. Astronomers point their telescopes toward nebulae, looking for answers among the stars. The Hubble Space Telescope gave us deep new vistas of the universe, but it is just one among many powerful eyes in the sky. Infrared observatories, such as Spitzer, and now the James Webb Space Telescope, peer through the dust to the cradles of star formation that had remained invisible. Huge ground-based telescopes with mirrors spanning tens of meters, equipped with adaptive optics to correct for Earth's atmosphere, dive deeper into the cosmic nursery with each generation. These ever larger observatories continue incorporating new sensors and techniques that sharpen our view. Radio arrays like ALMA listen for the faint hum of cold molecular clouds, the raw material that eventually collapses into stars. Each of these instruments captures a part of the story, revealing shapes and structures that are often hidden in visible light. By combining data from multiple observatories, astronomers create a richer, more complete image of the star-forming regions. In this way, technology helps us lift the fog of space and witness the birth of stars directly. Together, These telescopes form a concert of discovery, each playing its own role in the symphony of our cosmic understanding. In recent years, telescope technology has opened previously unseen corners of the universe. The James Webb Space Telescope, with its infrared gaze, has unveiled newborn stars still wrapped in blankets of dust. Radio telescopes such as ALMA detect the whisper of cold gas clouds and map the distribution of star-forming material. Meanwhile, X-ray observatories reveal how intense winds and explosions from stars sculpt the surroundings. Even high-energy gamma-ray detectors and neutrino observatories contribute pieces of the puzzle. The synergy of all these tools forms a multi-wavelength orchestra of discovery, each instrument adding depth and color to the cosmic scene. Together, they lift the veil on the early stages of star birth, letting us witness the delicate dance of gravity, gas, and light. These observatories are like time machines as well as eyes. Because light takes time to travel, looking deeper into space means looking further back in history. When we observe distant star-forming galaxies, we witness conditions from an era when the universe was young and the first stars were igniting. Some of the oldest light we detect comes from periods when only a few 100 million years had passed since the Big Bang. By studying these ancient images, we learn how the universe first learned to make stars. They show that the story of star birth has been playing out since the dawn of time, changing form but never ceasing. Each new telescope and instrument pushes this horizon further, continually rewriting our cosmic origin story. The advances in telescope technology are breathtaking. Large mirrors, precision spectrographs, and even telescopes in orbit have pushed the boundaries of what we can see. Each development peels back another layer of mystery from the stellar nurseries. What once seemed smooth now reveals jets, filaments, and clumps of gas. Scientists often use long exposures, stacking multiple observations, and sophisticated image processing to bring out faint details around protostars and nebulas. Every new detail helps refine our understanding of star formation, revealing the intimate steps in the cosmic cycle that were once only theorized. In this way, the pursuit of knowledge and our ingenuity with instruments become part of the story of the stars themselves. Astronomers have turned even the Earth itself into a telescope. By linking instruments across continents, like radio dish networks or the Event Horizon Telescope, we achieve resolution far beyond a single observatory. Proposed interferometer arrays in space promise to reveal even finer details of star-forming regions in the future. Meanwhile, planned projects like the Vera Rubin Observatory will scan the entire sky nightly, catching transient events in stellar nurseries. Every advance is like sharpening our vision. What was once a fuzzy glow resolves into a beautiful, complex cloud of knots and filaments. In this global quest for light, human ingenuity continues to illuminate the dark corners of our universe, one discovery at a time. Even amateur astronomers and enthusiasts join the quest. With small backyard telescopes, people track comets and nebulae, contributing to scientific observations. Public images from big observatories are shared widely, inspiring new generations to look upward. When ordinary citizens contribute data or even help discover new objects, it shows that the cosmos truly belongs to everyone. Our collective efforts turn the night sky into a communal classroom, open under the stars. Each telescope has its own story. Hubble, launched in 1990, was initially blurred by a flawed mirror and had to be serviced by astronauts, yet went on to revolutionize our view. The Webb telescope took over a decade from planning to deployment, with 1 million intricate parts unfolding perfectly in space to begin its mission. These stories remind us that exploring the universe takes patience, persistence, and human courage. Through setbacks and triumphs, our resolve to observe the stars has only grown stronger. Telescopes are to astronomers what microscopes are to biologists. Tools that extend our senses. Just as looking at cells revealed a new world of life, peering deeper into space reveals a vast and wondrous cosmos. Each technological leap has opened up an entirely new scale of exploration. From seeing individual galaxies to capturing the glow of the Big Bang itself, these instruments continually redefine our perspective. They remind us that humanity is inherently curious, always reaching for the horizon of understanding. When breathtaking images from these telescopes are released, they inspire people of all ages. They spark the imagination of children who may become the future scientists, writers, and dreamers. These pictures make us feel connected to the universe, bridging the gap between scientists and the public. In sharing the view, each telescope becomes a teacher, educating us about the night. Through their eyes, we all catch a glimpse of the heavens. With these tools in hand, let us turn to a famous nursery of stars. We will revisit the pillars of creation, a stunning example of the cosmic process we have been exploring. Here, in these soaring columns of dust, we can apply everything we have learned. Let us see how our technology reveals new secrets hidden in those pillars of starlight. Iconic scenes of the pillars of creation have been revisited with breathtaking clarity. This famous nebula, part of the Eagle Nebula, was once only a blurred wonder to early telescopes. The Hubble Space Telescope's original image in the 1990s captured the public's imagination by revealing colossal towers of cosmic dust lit by newborn stars. Those images showed a static, almost mystical scene, but that was just one moment in time. Now, decades later, our view is sharper than ever before. The James Webb Space Telescope's infrared vision pierces the dust, revealing structures and stars hidden behind the original columns. Each new observation adds depth to our understanding, showing how light and shadow play across these giants of creation. They remind us that what we see is only a snapshot of an ongoing process of transformation. New observations reveal that even these seemingly permanent structures are alive with change. High-resolution images show faint jets and outflows of gas streaming from infant stars deep within the pillars, slowly carving holes in the dust. Powerful radiation and winds from nearby massive stars buffet the edges, sculpting the dust into ridges and hollows of light and shadow. Astronomers have even detected subtle changes by comparing pictures taken years apart, hinting that parts of the pillars may be evaporating. Computer models predict that on cosmic timescales, these formations will vanish, turning into streams of stars. In this way, the pillars are not symbols of stasis, but reminders that even grand cosmic structures undergo transformation. Each new generation of telescopes refines this cosmic portrait. Like explorers mapping unknown lands, we map nebulae with ever-increasing precision. With each upgrade, from optical to infrared to radio observations, we learn that what appeared solid and eternal is in fact dynamic. The pillars of creation, named for their majestic appearance, are shown to be slowly eroding under the influence of starlight and wind. Their majesty lies not in permanence, but in the momentary splendor of creation and destruction intertwined. As our instruments improve, our view of the universe becomes more dynamic and alive. Each new discovery offers a deeper understanding of the cycles that shape all cosmic structures, reminding us that even the heavens are not frozen in time. The pillars of creation have transcended science and entered our culture. When Hubble first captured its famous image, people around the world recognized those towering columns of dust. It became an icon for astronomy, symbolizing the very idea of stars being born in cosmic nurseries. Now, scientists revisit this icon not for spectacle, but to learn from it with fresh eyes. The renewed scrutiny of such a well-known object highlights how our understanding is always evolving with technology. These pillars lie some 7,000 light-years from Earth in the Eagle Nebula. The light we captured from Hubble took 7 millennia to reach our eyes. As we gaze at the pillars, we are seeing them as they existed when the first human civilizations were forming. This temporal gap adds poignancy. We are looking into a distant past, yet our connection to it is immediate. The same physics shapes those distant clouds and our own skies, closing the cosmic divide. Understanding their distance and composition helps us see how they fit into the story of our galaxy. Within the shadows of the pillars of creation, new stars are coming to life. Dense clumps of gas within the columns collapse under their own gravity to form embryonic suns. Astronomers have spotted these protostars hidden behind the dust, some already igniting nuclear fusion in their cores. Others are still in earlier stages, enveloped in thick cocoons of gas and dust. These infant stars drive jets of material that carve narrow lanes through the nebula, like starlit tunnels. Each of these processes was hinted at in the original images, but our modern view brings them into sharp relief. Astronomers have observed these pillars across the spectrum. Infrared telescopes reveal stars and warm dust hidden behind the opaque layers, while radio observations map the cold gas. Ultraviolet images highlight the hottest newborn stars, ionizing the cloud's surface. Even X-ray observations can show how energetic particles carve holes in the pillars. Each wavelength adds to the portrait, like layering different brushstrokes to complete a painting. Together, these views confirm that the pillars are rich, stellar nurseries under dynamic construction. The newest observations from the James Webb Space Telescope have transformed our view of the pillars. Webb's mid-infrared camera peered through the dust, revealing hundreds of new protostars and young stars previously unseen. Astronomers report that tens of thousands of stars in the region now appear in detailed clarity. This wealth of data enables researchers to refine models of star formation. By counting these stars, we can test how quickly clouds collapse and how many stars should form. These findings illustrate how each advance in technology deepens our understanding of cosmic nurseries. Watching the pillars of creation evolve before our eyes is both majestic and humbling. These towering structures once seemed as permanent as mountains, yet on cosmic timescales, they are fleeting. What appears eternal is in constant flux, carved by the very stars that reside within. This balance of creation and erosion is a profound theme. The same forces that build stars also dismantle their cradles. The pillars of creation thus stand as a symbol of the universe's dual nature, creative and destructive, inextricably intertwined. They remind us that even the grandest forms must obey the laws of the cosmos. As we revisit these cosmic wonders, we appreciate not only the formation of stars, but also the passage of time itself. Each updated image is a reminder that our understanding of the universe is a work in progress. The pillars, like all celestial features, are not static backdrops, but dynamic stages in an ever-unfolding drama. With each new observation, we learn more, and we remember that our role is one of observer and student of the cosmos. Even as our technology sees more, the fundamentals of gravity and physics remain the same forces at work. In the quiet light of these images, we stand humbled, appreciating how the universe gradually reveals its wonders. Aside from the pillars of creation, astronomers study many other iconic nebulae. The Orion Nebula, the Carina Nebula, and others reveal star birth in different environments. Each nebula has its own shape, but all share the same processes we see in the pillars. By comparing them, we learn how factors like the mass of surrounding stars or the density of gas influence star formation. Together, these cosmic nurseries paint a fuller picture of how and where stars are born. The pillars themselves are part of a larger cosmic environment. They lie in a star cluster filled with young, massive stars whose radiation lights up the clouds. These neighboring stars help make the pillars visible, but also gradually evaporate the material. Understanding the role of these nearby stars helps explain the pillar's shape. This context shows us that even within one nebula, many forces are at play in sculpting the regions where stars form. Scientists have even used data from these observations to create immersive visualizations. 3D renderings of the pillars allow us to fly through the nebula in virtual space. These simulations take the astronomical data out of two-dimensional images and into an interactive experience. They remind us that although we cannot travel to these distant clouds, our imagination can explore them. Such visualizations bring the pillars of creation closer to home, letting us feel surrounded by the birthplace of stars. The pillars of creation are not unique. Similar star-forming columns exist elsewhere in the galaxy. By studying many such nebulae, astronomers piece together a general theory of how clouds collapse into stars. Every new pillar, or dark nebula we image, adds another piece to the puzzle. Taken together, these observations show that creation occurs throughout the universe, not just in one iconic site. In this way, the pillars serve as a gateway, linking a single famous image to a vast tapestry of star formation. Truly, the night sky is full of wonders, each telling a part of the cosmic story. Thus, the pillars of creation teach a simple lesson. In the universe, birth and change are one and the same. From these lessons of cosmic architecture, we shift our focus inward. We see that even our own existence is part of this larger tapestry. The next journey is from the grand to the intimate, tracing those cosmic threads into our own story. We ourselves are threads in this vast cosmic tapestry. Every atom in our bodies was once forged in the heart of an ancient star. In the darkness of space, long before Earth existed, nuclear furnaces in dying stars created the carbon in our cells and the oxygen we breathe. They produced the iron that courses through our blood and the calcium in our bones. Our very DNA is written in stardust, linking our existence to the far reaches of the universe. This fact connects us directly to those distant processes. We are children of the stars in the most literal sense. The universe crafted us from its own materials, weaving our being into its eternal story. What this means is truly profound. The stuff of the cosmos flows through us all the time. Realizing our cosmic origin is both humbling and inspiring. In a way, we carry stardust in our veins with every heartbeat. This deep connection dissolves any sense of separation between us and the night sky. The same physics that ignited a distant sun now powers the rhythm of our hearts, silently linking our story to the cosmic drama. When we gaze at the stars, we see light from the past, and we see ourselves reflected in that distant glow. The stars above are mirrors of our own origin, each one whispering that we all come from the same source of creation. The cycle of creation continues as it always has. New stars ignite from the remains of old ones in an endless relay. Eventually, these stars will also die, fueling yet another cycle of birth, death, and rebirth. In this endless wheel of cosmic time, Nothing truly vanishes. It only transforms, passing its legacy forward. Every element in our bodies, every breath we take, is part of this cycle of renewal. In this way, our existence is woven into the continuous pattern of the universe's self-renewal. Scientific understanding thus brings us closer to the mystery of being. It fills us with wonder to know that a distant supernova or collapsing cloud set the stage for our existence. In every particle we hold, in every heartbeat, the cosmos keeps its ancient promise of renewal. This profound connection shapes a worldview where humanity and the universe are not separate, but parts of one continuous story. Under the vast night sky, we find meaning in our smallness and significance in our origins. Understanding that we are all made of stardust both humbles us and connects us to the eternal universe. Through science, we have peeled back layers of mystery, yet the more we learn, the deeper the wonder grows, echoing the infinite nature of the cosmos. Imagine tracing each atom in your body to its cosmic origin. The hydrogen in our veins was born in the Big Bang. The carbon and oxygen in our cells inside earlier stars, and the gold in our jewelry inside distant explosions. Even the phosphorus that nourishes our cells and the calcium in our bones came from nuclear forges far beyond Earth. Scientists have measured the proportions of these elements and confirmed that nearly all of the building blocks of life come from stellar processes. In a way, every heartbeat we feel is powered by atoms that once shone brightly in other stars. This isn't merely metaphor, it is literal truth written into the fabric of the universe. Our solar system itself is a second-hand creation. When the Earth and Sun formed 4.6 billion years ago, the gas that clumped to form them had been enriched by many previous generations of stars. Traces of short-lived radioactive elements in ancient meteorites show that a supernova must have occurred just before the Sun's birth. That supernova's shockwave likely triggered the collapse of the gas cloud that became our solar system, bringing with it fresh dust and elements. In this way, we were directly shaped by the last gasp of an earlier star, born from material older than our planet by eons. We are the offspring of a lineage of stars, one branch in a family tree that spans the galaxy. This knowledge crosses borders and ideologies. Regardless of who we are or where we come from, we all share this cosmic heritage. The atoms in an African child, an Asian rice farmer, a European poet, and a South American warrior were all forged in stars. Looking up at the night sky, every person sees the same story of creation. When we learn that our building blocks come from the cosmos, it instills a sense of unity and perspective that transcends cultures. No matter our differences, we find a common bond in the stars above. Realizing this can be a source of comfort and wonder. It reminds us that, in a vast universe, we are not mere accidents, but part of a grand design. Our origins are universal. The same physics that created galaxies also runs in our hearts. This cosmic perspective can shift how we value life and our responsibilities. Knowing we share our essence with distant stars encourages us to protect our planet and value each other. In this way, science not only explains our origins, but also enriches our sense of purpose. Consider the timeline. Atoms in your body have existed for billions of years. They have traveled through different stars, interstellar clouds, and now through you. We are a temporary vessel for these eternal travelers. In understanding this, time itself takes on a new meaning. Our brief lives are part of a much larger saga that stretches from the Big Bang to the distant future. Humanity has always looked to the skies, seeking to understand our place in the cosmos. From ancient astronomers mapping the stars, to modern scientists probing atoms, our curiosity has been relentless. Each generation inherits a deeper understanding from the last, as if passing on a cosmic legacy. We stand on the shoulders of thinkers like Copernicus, Newton, and Sagan, who saw that Earth and its people are part of a grand story. This legacy reminds us that learning is a human birthright, and the universe is the classroom open to us all. It is remarkable that this star stuff became self-aware. Somewhere in the vast universe, matter rearranged itself to form thinking beings gazing back at the stars. In each person, the cosmos contemplates itself, a loop of existence from atoms to awareness. This cycle of reflection reminds us that we are not just observers, but also participants in the universe's story. Our questions and dreams are as much a part of the cosmos as our molecules. Our understanding has grown, but many mysteries remain. We know now that our atoms have traveled light years and lifetimes, but questions linger. What is consciousness, and how did it arise from star matter? As we seek these answers, each discovery reveals how special and ordinary we are. In both our insignificance in the cosmos and our connection to it, we find wonder. This journey of discovery is ongoing. With each passing generation, our perspective will broaden further. In the chapters to come, future astronomers will take up the mantle, telling new parts of this endless saga. For now, we stand at this point in history, filled with awe and curiosity, under the same stars as those who came before and those yet to be born. The night sky belongs to all of us. Throughout history, every culture has looked up and been captivated by the stars. Ancient astronomers drew maps of the constellations, building myths to explain what they saw. In every corner of the world, we find stories of creation written in the stars. No matter how different our lives may seem, under this blanket, we are united by a common wonder. Every child who looks up in awe is connected to people who lived thousands of years ago in the same way. When brilliant events like a meteor shower or a total eclipse happen, people across continents pause and look upward together. They may speak different languages, but they share the same sky and the same sense of wonder. Telescopes might be far away, but the vision is personal and communal. This bond over the sky reminds us of our common humanity, even when we stand under far-flung and diverse heavens. The cosmic perspective holds a silent solidarity among us all. In the future, humans may settle other worlds and build new observatories on distant planets. Still, they would be under the same stars, looking back at Earth as a pale blue dot. Astronauts who have gazed at Earth from space report a profound change in perspective, realizing how interconnected everything is. From orbit, borders disappear, and the Earth shines softly under the universal lights. In this expanded context, our connection to one another and to the universe becomes even clearer. Understanding our link to the cosmos also carries a responsibility. Earth is the only home our species has ever known, and it exists under these stars, just as we do. Knowing we are part of something so vast gives rise to both humility and hope. We realize that preserving our planet also preserves our connection to the universe. Caring for our world is a way of honoring the cosmic heritage we carry within us. When we understand our cosmic heritage, it can change how we treat each other and our planet. We come to see that Earth's diversity of life reflects the diversity of the cosmos. Each species, each individual, carries molecules forged in stellar furnaces. This knowledge can inspire us to protect our home and one another, knowing we share a common origin and fate. In our daily lives, this understanding may seem distant, but its implications are real. The same curiosity that drives astronomers fuels innovation in technology, culture, and thought. By looking up and learning about the cosmos, we broaden our perspective on what humanity is capable of. Our shared sky encourages us to dream bigger, remember our unity, and embrace the unknown with excitement. We have traveled from the farthest filaments of the cosmos to the atoms within us, and through it all, we remain under the same stars, looking upward in wonder. Our journey through this part of the universe's story ends for now, but the sky remains open ahead. The next part of our exploration will take us even deeper into the mystery of creation. As we proceed, we carry the memory of these pillars and threads with us, always under the same stars.